Thank you. Yes, we can see your screen. And if you could just say a couple of words just to make sure that the audio is okay. We're very
Yep,
sorry that you had to.
Not a problem at all. Thank you very much for having me again on the
Yeah,
line. And it's
you're
an absolute
audible
pleasure.
loud and clear. This time it's okay. Perfect.
Great, perfect.
Okay. I will. We're still waiting for Martin. I think he's caught up in traffic. So maybe another 5 minutes and we'll go.
No worries. I'll just let me know.
I'll let you know. I'll let you know.
Thank you.
Uh, we are ready to get started with the second day of this Mars workshop. And we have a bunch of online and offline talks. So the first presentation will be an online presentation by Katerina Milkovic and from Curtin University. So over to you, Katerina.
Thank you, Rama, very much. Hello and good morning, everybody. And it's my absolute pleasure and honor to open day 2 of the workshop. And apologies again for not being able to be there in person. This presentation will be about hydrothermal processes in impact craters on Mars and tracing hydration in the Martian crust. I'm aware that yesterday we had quite a few presentations that touched on the hydration in the Martian crust and the past and present evidence of water and subsurface ice. So I would like to focus more today on craters specifically. But before we go, I would like to just briefly introduce them. And this chart is appropriate for the Earth, but it serves the purpose to demonstrate the frequency of impacts. So big impacts, they happen very rarely, and the so-called impact basins, the largest impacts that happen on Earth, they happen on Mars as well, are only reserved for the first billion years after planetary formation. Whereas what we heard a little bit about yesterday when we talked about mass quakes that came from fireballs in the sky, they happen very, very frequently. And we had, during InSights operations on Mars, over 30 impacts in 4 years of operations. And if you look in the night sky from where you live, then you might get lucky to see one fireball a night on Earth. So when we talk about really cratering and impact process that might be relevant for hydrothermal processes, we actually want to focus for them in some kind of a middle bit. So I don't know if you can see my mouse, but that's okay. So these are the 3 stars in the middle that kind of represent here the mid-range or mid-age as well of impact craters. Yes, it is showing Earth craters, but we do have equivalent craters on Mars as well. So for example, Curtin crater in Canada is a crater that has hydrothermal processes that I will touch on a bit later. So these are the so-called mid-range complex craters that have been observed on Earth to have hydrous alterations or hydrothermal alterations in their faults. And we're also observing them on Mars as well. So they don't happen very often, and they are generally reserved for the older Mars than younger Mars. So craters form by a projectile striking the surface at very high speeds and inducing a shock wave or a very fast pressure wave going through the target that causes the compression and compaction of the target, and the material gives way. So the ground is compressed down and stuff that's near surface starts to be pushed out, and the crater grows and while it's growing, it's also causing the material within the crater to potentially melt and potentially vaporize, depending on the size of the impact. Material is excavated and forming the ejector curtain. And the crater grows until the kinetic energy of the impactor is completely spent. In numerical world, where we do numerical impact crater processes, we call this moment transient crater, because that's when the impact energy is completely spent and the kind of cavity in the ground is the largest. So that's when the moment in time when the crater stops growing and starts collapsing. We start a modification stage that then causes material that has been pushed out, then starts to slump in from the collapse of the crater walls. In a simple crater formation context, where we have a ball-shaped crater in the ground, we're forming so-called breccia lens and a ball-shaped crater in the ground. For those maybe familiar, those we have a meteor crater in Arizona, which is one of the famous ones. We also have a bunch of those on Mars. We also have Luna crater there in India. That is also a simple crater, similar size to meteor crater. But these are not that exciting in terms of causing hydrothermal processes because they are still a bit too small. If we go size up to complex craters, they're specific because the transient crater, that crater in the ground before the crater collapses, is a touch too big, so that instead of just causing the effect of crater wall slumping down, we also get the bottom of the crater rising up. So the resulting crater is not a ball-shaped hemisphere, but it's actually more flattish, and it's got a central peak protruding in the middle of the crater. And those are the interesting features that we will explore a little bit more. In terms of modeling, and that's some of the stuff that I will mention today, we use shock physics codes, but in terms of impact cratering process, it is a unique geological process, the only one that's actually truly dynamic and happens in an instant compared to other geological processes. And in doing that, the projectile bearing into a target, into the crust, into a rock, causes melt, causes a shock metamorphism, causes fracturing and brecciation of the crust further away from the impact point. But also it redistributes the crust, it redistributes material in the top crust by ejection and collapse of material. For the purposes of some of our work, we use the ICEL shock physics code that can actually track the compression, compaction, ejection, excavation of material, as well as the pressure and temperature changes in the target rock. And through that, we use various equations of state for geological targets, typical geological targets, but we can also work with multi-materials and a various number of constitutive models appropriate for different planetary surfaces. I will show you some of the 2D results, which means that we're simulating our crater formation as in a cylindrical symmetry. So we're only simulating a vertical slice of a half crater, if you will. Okay, in terms of connecting the dots a bit further away, resources in craters, there's a couple of things that are important here to note that would then cause some hydrothermal alteration. We do need water, and near surface, we see water ice. Here are some examples of where water ice was obvious on the surface of Mars, underneath the Mars lander, Phoenix Mars lander. There were slabs of ice being exposed just by thrusters as the spacecraft was descending in the polar regions. But also it was visible by just simply scooping up the soil in the polar regions, and ice was right there within a few centimeters under the soil. The interesting bit here is that ice starts to sublimate immediately as it is exposed to the surface because of the low surface pressure on Mars that goes straight from solid to a vapor. So it sublimates immediately, as opposed to Earth, that it wouldn't happen because we have a high surface pressure. So we know we also have changes in the frost in various other regions on Mars and so forth. So we also know we have freshly exposed impact craters, the fresh craters that have exposed ice. And the reason we know they're fresh is because the moment they expose ice on the surface, that ice starts to sublimate. So if we see an icy small crater on Mars, we know it's fresh because within the minutes or months, that ice will be gone, as you can see here by the two staggered photos of the same crater. Normally, we see those freshly formed craters in the dusty regions because they're small and they need to be observed from orbit. And then so if they're small and they're formed in the dusty region, the halo of ejecta will be quite large. So that's how they're easily spotted in the dusty regions from orbit. I mentioned this yesterday. that we know that there is a continuous shallow ice within the first top 30 centimeters of regolith in high latitude polar regions on Mars. There should be a discontinuous shallow ice within the top 5 meters on the surface in the regions of like mid latitudes, but it's highly believed that there should be no ice in the equatorial regions, regardless of the depth. Okay, so where does mineralization come to play, right? So I will focus a little bit more on the complex craters, specifically on Mars. They are between 6 or 7 kilometers in diameter, up to about 90, because smaller than 6, they are simple and they're not big enough to cause subsurface alterations or excavate something that's altered in the subsurface if it's not ice. And if they're bigger than 90 kilometers, they still could be included in some form of hydrothermal activity, but then we also have to deal with a lot of melt and a lot of heat produced in the crater formation. So let's look for the time being in this kind of middle range. On Earth, this is actually a very good interpretation or a cartoon showing where one could expect to have some form of alteration visible at the surface. It's usually in the faults, faults that form during the collapse of a complex crater. This is an interpretation of a Horton crater, but nonetheless, it is an example of a complex crater with a central uplift that is equivalent of Horton on Earth or a slightly bigger crater on Mars. So we've done some modeling for that, and while in the middle of the crater, where you can see mostly in this red outline in the top left, it is the main melt pool surrounding the central peak with some broken breccia inside. And then there are faults forming beyond the melt pool and into the terraced rim, where we could also have fractured patterns to promote fluid flow. What you see on the bottom left is some work done by my postdoc that is looking at fracture patterns from the shock physics code as they're extending radially away from impact in some form of shallow surface. But also everything that's in red here, you can't really see the scale, apologies. Everything that's in red is very, very fractured. And then you can see the fracture pattern radiating away from the impact point as well. And that is important because fractures create voids, and then voids enable then for gas and fluid to permeate. And the one on the top right is a temperature plot, which suggests that the central part of the crater is very hot. It's this kind of molten or semi-molten central uplift that is then surrounded by a little bit of melt, and that's where some of the material has been uplifted from underneath as well. So the reason this is interesting is because there are we need heat and we need fractures that are caused in the cratering process in order to in any way engage any buried groundwater. So we need, as I said, we need faults and fractures to enable the fluid propagation or permeation of any materials, and we need heat so that any mineralization can form. Too much heat will destroy any mineralization that's already there, but as this kind of crater cools down, then there will be a lukewarm environment at some point, if you will, that will be perfect for new mineralization to form. Then here is from geophysical modeling. Various authors have looked into that as like what would be the stable cryosphere depth. Some authors have looked at stable water table depth, the stable cryo depth. And typically what we see is that The stable tables are actually, I'm going to show you this one. Are at deeper depths at poles and shallow depths at equatorial region. But if we look at geophysical modeling and thermal evolution modeling of Mars as a whole over time, that depth actually increases. So basically the stable cryo depth or stable groundwater depth actually increases as Mars cools down. So in the ancient Mars, it was the water or ice could have existed in a stable way in shallower depths than as we move more closer to the present day, which suggests that craters that are formed on an older Mars, that are older craters, are more likely to be subject to hydrothermal processes than the younger craters, simply because they have sampled during their cratering process depths that could engage with any fluid or ice, if I'm being clear. Some of numerical modeling that is not super straightforward to understand, but the left column shows changes in temperature in a complex crater. Middle column shows the exact temperature as measured, and the right column shows stratigraphic change, which if you see in vertical offset in horizontal lines, that suggests the formation of fault lines. What is interesting here is that these are the three different crater sizes, 20, 40, and 80 kilometers in diameter. They kind of cover that entire complex crater range, and suggesting that 20-kilometer crater might be just a touch too small to cause any meaningful temperature changes, whereas the 80-kilometer crater might be a bit too big to retain any hydrothermal mineralization that's already there during cratering process. So this is a dance between impact excavation and impact generation and impact destruction of pre-existing hydrothermal mineralization that was already in the crust, but also enabling environments to form new hydrothermal mineralization as after the crater formation. An interesting topic of interest is the Tor crater. We've done some work on that side. It's definitely not the only crater that has been pegged to have hydrothermal minerals in them, but it's here near Nili Fosse and also near Isidis Basin and near Jezero crater where Perseverance is. So that's an interesting part of Mars. We've looked at some of that local stratigraphy and geology, and have looked at slopes and roughness of the terrains and elevation in attempt to provide further guidance of where could we maybe go and land in that region. These are the CRISM interpretation data overlaid to DMIS and visual imagery that have recorded some of the hydrothermal mineral assemblages around the central peak of the crater, not on the central peak, but around it. And that has been somewhat justified by impact modeling by trying to discern whether these deposits were impact generated or impact excavated. And the jury's still out in some ways, but potentially some of the higher, some of the mineralization that is resistant to high temperature alteration could still exist there, but our results suggest that it would be something that has happened after Tora formation. In terms of what could be excavated, we are also looking at the amount of material that's been excavated. And I guess here, the most important is this histogram at the bottom, where we suggest that a big fraction of the ejecta, 33 and 43%, is actually not being shocked enough or heated enough before it falls around the rim into this proximal ejecta blanket. So if we're looking for hydrothermal mineralization that is within complex craters on Mars, then looking at the ejecta blankets is probably some more likely place where pre-existing mineralization could be found. Whereas if we look at the central parts of the crater, we might be looking at mineralization that happened or formed after the crater has formed. If I had to really like pick favorites, that would be my pick. Just to kind of wrap things up slightly with a slightly different flavor, I'd like to point at this really comprehensive paper recently published in PEPI that is around porosity and hydrosulfuration in Martian crust as seen through the eyes of insight. And that paper has done an in-depth analysis of basically the region that was around InSight, which is pretty large, that there should be evidence of present-day fluids in the Noachian sediments at up to 2 kilometers beneath InSight. And there are evidence aqueous alteration affected the whole crust around InSight. And there is sufficient porosity throughout basically half the crust on Mars. And that we could say that porosity and alteration dates back to Noachian. So I encourage you to read that. It's pretty long and it's pretty detailed and it's pretty awesome. The one thing that might have not been mentioned yesterday, but it's very interesting to just keep in mind that we still haven't moved away from theory that Earth and Mars have started to evolve from a similar standpoint as planets, and that in the first 500,000 years to 1 million years, half a billion to a billion years, the Moon and the Earth and Mars might have been very similar as planets with the surface, free-flowing water, dense atmosphere. But Mars, being a much smaller planet, actually evolved faster in a sense and has started to lose its atmosphere and magnetic field, and with that actually have cooled faster than Earth. So something interesting to keep in mind as a form of this diagram. And I'd like to stop here and ask if you have any questions. Here is a bit of here's a picture of Dry Valley on Antarctica, which is not Mars, but looks very much like it. So thank you very much for your time.
Thank you very much. That was a fascinating talk. So we'll open it up for questions, and there are plenty. Hold on.
Good morning. Very nice talk. This is Prashanjit from IISc Bangalore. So I have one question regarding your melting. So now if you think of inducing melting through impact, one of the important aspects which is different from Earth is having large abundance of carbon dioxide. So now if you think of the role of carbon dioxide in inducing melting at little bit lower temperature and producing what you showed somewhere around 1400 degrees Celsius based on the simulation, what is the role of fluid in terms of inducing the melting of such kind of process of cratering and hydrothermal outpour?
Right. I am not entirely sure I heard the whole question, but strictly speaking, the melting, the shock melting is dependent on the rock type that the shock has been exposing to. It should not have anything to do with the atmosphere. So
I am talking about fluids. I am talking about the fluids which are present there as a form of water or carbon dioxide, which eventually will come
inside the melt or
at the point of impact. You will have a lot
in
of
the
clay
crust
minerals,
or on the surface.
which you will have clays which are going to produce a lot of water. You will have other materials which are like maybe siderite, which has a lot of carbonates, which might produce a lot of CO2. this will have effect in terms of inducing melting process when you have impact.
Correct.
The
Correct.
fluid
Yes, absolutely.
interference, yeah.
Yes, so absolutely. So what we do in impact simulations is we assume that our crust is a single type rock because that's how much we can do in the shock physics code we have. So all of the equations of state we use are relatively simplistic, but they're based on numerical on laboratory experiments of how basalt, for example, behaves at high pressures and temperatures when it's exposed to shock. So these are difficult to compose, those equations of state, and they're purely experimental from the laboratory, and everything else is then extrapolated. So we've made some progress in computing those equations of state for mixed materials, which is why I think where you're going with this. So we could then start producing mixed materials where we have a little bit of basalt, a little bit of ice or water, a little bit of carbonate and minerals, and then in different fractionations, and then create a completely new equation of state that we then feed into the code. That would probably answer your questions a lot better because I don't have the answer immediately off the top of my head, other than doing a bit of back of the envelope calculation where we know what will be the expected pressures through the crust and then work out the pathway for release of fluids and changes of phases in carbonates and minerals.
Okay, thank you.
Hi, thank you for the nice talk. So I have a couple of related questions. The first question is that one of the plots that you had shown where you show that the depth of the cryosphere near the equator is lower, whereas it's much higher as you go towards the poles. If I'm not wrong, it's about 3 kilometers closer to the equator, and then you show that it goes almost to 10 kilometers closer to the poles. So my first question is, how would you explain why the cryosphere is found much deeper at the poles compared to the equator? And a related question is that, does it mean that when you look for these hydrothermal signatures, can you find them at smaller craters near the equator, whereas you need to start looking for those signatures at much larger craters as you go towards the pole?
Sorry, can you repeat the second part of the question? First one is around the cryo depths, and the other one?
So the second one is about the size of the craters where you can find these hydrothermal signatures, and its dependence on the cryosphere depth. So is it that you can look for these signatures in smaller, simpler craters closer to the equator, and do you have to search for them at much larger, complex craters towards the poles?
Understood. Thank you so much for repeating that. The scale for the cryosphere depth should have been reversed in alignment with the water stable water. This is a tongue twister. Stable water depth, groundwater depth. So it is deeper on the equator than it is on the poles. So it's the other way around. I can double check all that and send you some information. But what is more interesting is because the planet is cooling, or has been cooling since its formation, that the depth to the groundwater stable table is going deeper into the planet as we go from old Mars to present day Mars. So as the planet is cooling, the ability to preserve stable water underground is going deeper and deeper and deeper. So I think the scales are a bit different because it's talking about how deep something needs to be and the depth too. So it looks reversed. I would say maybe for your second question, instead of thinking how big the crater needs to be, instead of thinking do you need to be in the equatorial or polar regions, I think the question is both. It needs to be, the question is about how big it is, meaning how much of the crust you would sample, as it's forming, but also what's the age of the crater and where on the globe it is. So all three factors play a role. It's not either or. Because if we assume that there is stable groundwater somewhere, and then it's decreasing or it's different across the globe, and it's different based on the age of the crater, and different size craters sample different depths, then you have to work out all three parameters.
Okay, I had a quick question before we move on to the next presentation. So you also showed a diagram on the stability of water on Mars. And I think it doesn't take too much to sublimate the ice, right? If you
Yes.
had one of those. And so if you look at cratering events on Earth, I mean, we'll find that it is almost impossible to, find the projectile that hit the surface be preserved. Everything gets vaporized. And so if we translate that information to other craters and other planetary bodies, do you think that by hydrothermal, it is more like steam that's interacting with the rocks rather than heated water?
It's most likely, depending on, it depends on, thank you for your question. So it really depends on the size of the crater and how much temperature change the cratering process experiences. So if we have small craters, you might not even reach a melting point, and just you break the rock and rock goes just out. And I've shown you yesterday that 150-meter crater on Mars that excavated fresh ice in the ejecta. There was no heating there. There was no melting there. There was heating. There was no melting, and there was no vaporization. But for the bigger the crater, the more heat is deposited, and surely there will be bigger fraction of the crater that goes above melting temperature, therefore will cause anything that's icy or a liquid water phase. It would obviously go into vapor, and minerals will get vaporized as well. This is the point of where we start thinking about mapping out craters and understanding what's happening with them. So it's not a simple answer. It is actually a common misconception to think that all projectiles get vaporized. That's not necessarily the case. We've actually have quite a fair few even craters on Earth where they were made by an iron-rich meteorites, and those bits have survived the fall.
Yeah.
And we've seen, we've done heaps of simulations that also show that at what conditions the projectiles survive and how much. So it doesn't always go into pure vapor if it's something like Earth or even Mars impact, because average impact on Mars is about 6 to 12 kilometers per second, and in those conditions, regular rocks or carbonated rocks or carbonaceous rocks would survive the fall.
Sure. Okay. Thank you so much for your presentation again, and we'll move on to the next presentation, which is going to be in person. So is it Rajesh and Asif? Thank you.
something that is not. Yeah. Good morning, all of you. So first of all, I'd like to thank Professor Ramananda, Dr. Shyama, and Martin, the organizing team, for giving us this opportunity to be part of that India Mars Science Workshop. The title of our presentation is Geomorphological Analysis and Designation of Krishnan Crater in Sante Terra and Insights from Orbital Observations. So actually, Professor Ramananda has requested us that more audience will be from students' side. So the part of this presentation, it has been prepared as a very fundamental aspects. I think that will be too fundamental for the experts present over here. So please apologize for us that one. So the talk division is like this. Initially, we will give us some fundamental aspects like the Mars and planetary context, then the geomorphological approach, then the dominant processes like impact cratering, etc. So I will take care of these aspects, and Asif will take care of the study region in Santa Terra, and we got the opportunity to name one of these unnamed craters in that particular region, and also that scientific outcomes. So that part will take care by Asif. So coming to the context, okay, so why we are studying Mars, okay, so this is especially for students, okay, so there are like three reasons, the reasons are like scientific reasons, strategic reasons, and practical reasons are there. In that scientific aspects, of course, like a lot of discussions are there regarding the origin and evolution of life, then potential habitable aspects on Mars, and that water and mineral resources, especially for in situ resource utilization, etc. So these are the major scientific aspects. Then the strategic one, so this is the most accessible extraterrestrial body, that is that nearest planetary body to our Earth. Okay, so it has, yeah, so the past climatic variabilities and also like a complex geology. The complex in the sense that like same as that of our Earth, like, okay, so it also has diverse geological processes which has shaped up that origin and evolution of Mars also. And moving towards the practical reasons, we have scientific and technological advancements, and also the economic and geopolitical significance are there. So these are the major aspects the planetary community is looking forward for Mars. Sorry. So now coming to that geomorphological aspects. Okay, so we consider that that is one of that important tool to understand the planetary evolution sequence of the Mars, mostly using that geomorphology. Okay, so we can understand the landforms and surface processes which are formed due to diverse geological processes. So this is very much important, as we all are aware, like in situ data or in situ like field observation from Mars are like very limited. In that case, like orbital remote sensing data or like a high resolution data sets from satellite imageries help us a lot in identifying various geological features or the morphological features, that one. So the geomorphology role is that using that remote sensing data sets, we can have like identification, interpretation, and finally comes up to that evolution of a particular region or entire Mars also. So we can have, using this technique, we can have the reconstruction of climatic processes, hydrology, then hydration aspects, then other aeolian, fluvial, glacial processes, etc. So we have also worked extensively on that Eos region on Mars. Okay, so and identified. So this is from the, this is that Eos region and a portion of a Martian map. Okay, so using that data sets, okay, so we made valuable interpretations and identified the processes and finally come up to a model like this. So these geomorphological aspects are very much important or significant in understanding the interpretation of landform evolution through the climatic cycles, mostly in the case of Mars, driven by or this one orbital obliquity in Eos. So coming to that division of geological processes on Mars, we know that like we are having endogenic processes and exogenic processes also. So so the endothermic, it is mostly that energy absorbing one. Some of those examples for that, like, okay, the sublimation of volatiles, then thermal weathering, permafrost, and the cryogenic processes. So in the previous speaker also discussed about the sublimation of water ice, or here we can have that seasonal sublimation of carbon dioxide and water ice from polar caps or other regions. Then these type of activities can lead to formation of gullies. This is one important aspect as far as Martian craters, etc. are considered. Okay, so then surface collapse features, which can give rise to various morphological features. And here you can notice that development of seasonal dark streaks also. So moving to that thermal weathering aspect, okay, so it experiences extreme diurnal temperature variations and underwent so day and night contraction and expansion, okay, so which can lead to weathering, formation of regolith, etc. And the permafrost or cryogenic processes like ice, it's an important process, okay, on Mars, okay, so surface or subsurface ice, then occasional melting, which we have discussed recently, okay, which can lead to formation of diverse landforms like polygonal ground cracks, then thermokarst-like features, and also etc. So these are some of the examples of endothermic or energy absorbing features on Mars. Now coming, okay. Sorry. So now exothermic aspects, okay, so that is that energy releasing one. So we have fluvial processes leads to development of several or enormous valley network. Okay, so yesterday's session, we were discussing about modeling that water budget or hydrological aspects of Mars. Okay, so these are very much important in that one. Development of catastrophic flood events leading to outflow channels, deltaic deposits, and associated mineral deposits are also very much important to understand the fluvial and that hydrous alteration processes. Then the glacial and periglacial processes leading to development of low-bed debris aprons, then lineated valley fills, polar layered deposits, etc. Then many of us are working upon that tectonic processes leading to Mars. Okay, so we all know that the plate tectonic processes are either operated very shorter span of time towards the earlier stages of Mars evolution, or it might not have been there. But we have a lot of tectonic, or we consider that intra-tectonic processes are there that leads to the formation of rift systems like valles marineris, then crustal extension. Okay, so that can lead to mantle upwelling, then heat, volcanic loadings, etc. And also can lead to formation of, or trigger the formation of giant volcanoes like Olympus Mons, etc. Then this aspect impact cratering, just now we had a very detailed discussion on impact cratering processes. So I will not be going into much details of that one, but I will also discuss some aspects or significance of that impact cratering processes on Mars also. So these are caused by meteoroids, asteroids, comets, etc. Then we have noticed that it can lead to development of simple crater, complex crater, and then multi-ring basins, etc. And moving to that physical aspect, it is also important understanding that physical processes like shock wave related aspects, melting processes, etc. Okay, so this we consider that this also one among the primary landforms. Okay, so which straightened up the superficial processes of Mars. Okay, so these are the craters that dominated Martian surface. Okay, so again a lot of indicators are there. For example, if you are having ejecta materials, okay, so those are a mechanism through which we can have some of the materials from deeper side exposed to the surface. That is one aspect. Okay, so then morphological diversity of impact craters are very much important. So that is also important to have this one age dating of a planetary surface also. So here you can notice that darker regions or darker shaded regions have less number of craters when compared to region outside that one, or region enclosing this one, which is having large number of impact craters are there. So we can use that crater density to understand age of the surface of Mars also. So that is one important aspect about that one. And again, we have discussed the crater counting technique, etc. Also, this is an important region for exploring various mineral resources, biosignatures, and it has a very importance in this one astrobiology related studies on Mars also. So what are that indicators from that impact craters? If you are having that eroded craters, we can understand various processes like aeolian or fluvial activities. Buried craters are there. Again, we can consider aeolian or volcanic, then sedimentary resurfacing, etc. Deformation, okay, so can lead to that tectonic activities, etc. Then if it is in a fluidized terrain, okay, so there also we can understand that possible presence of subsurface ice or volatiles. Then layered ejecta materials are there, which can lead to understand that interaction with volatile rich materials also. So this already we have discussed, okay, the physical processes which can lead to shock metamorphism, crustal properties like strength, layering, etc. Again, this depends upon the type of material on which the target materials upon which impact processes are taking place. Then that energy released during impacts, okay, the formation of central peaks where we can have exposure of deeper materials on the surface, multi-ring basins, etc. Okay, and yesterday we had a lot of discussion about that astrobiological significance also. For that purpose also, impact craters contribute a lot. Because it can generate heat leading to formation of hydrothermal system. A sort of like extreme environment can be developed over there, which could lead to formation of some microbes which can thrive in extreme environmental conditions. Okay, so it can create temporary habitable environments. Okay, so there can be development of like ancient lakes. Okay, those are also very much important for astrobiological point of view. Okay, so there we can have like a preservation of biosignatures or organic materials there. Then for mission planning aspects also, impact craters are very much important. Okay, so they are helpful in identifying that safe landing zones. Then disaster related studies like where like quake activities are there, whether it is safe to land on that particular region. Then sometimes like we are having that younger surfaces, safer, like fewer hazards are there, and older terrains like having more scientific information are there. So now that important aspect, okay, so selecting the right latitude to the study. So you can notice that because of that high, this one, sorry, majority of that landings, okay, so took place towards that low to mid latitudinal regions. The several reasons are there, like Martian obliquity variations, like which can drive ice to mid latitudes that can modify the crater morphology. Okay, so that's the main reason, like for focusing on lower latitudes region. And another significant aspects are there, like we can have surface age exposure because that regions are mostly less mantled by ice or dust than compared to that higher latitude regions. Then like mineral preservation. So we have seen that the majority of that hydrous minerals are preserved mostly towards that equatorial regions, etc. So no pervasive glacial modification, better retention of aqueous alteration processes or minerals. Then accessibility for future missions also because of lower thermal extremes, easier landing and more sunlight from solar power. And it can also use for like a comparative planetary related studies also. So this is one map that shows like various landers on Mars. Okay, so from one, okay, so majority of that landing took place in this particular region. Okay, and then like our study area, that is the Sante terrain, that also fits perfectly within that rover proven latitude band. Okay. So this is that Sante Terra region. Okay, so this is like one among the several low to mid latitude regions where we have we have investigated. Like okay, so this is the region, and this also has been previously considered in many missions as a potential landing site. It has you can notice that it is proposed but not selected. Okay, so that region is significant for assessing that past habitability. Then in ExoMars also it came up to semi-final and later it got eliminated. And again the target is like search for biosignatures also. And coming to that geological aspect, as it will discuss in detail about that one. So geological diversity, we are having like a chronologically diverse landscape. We are having Noachian cratered highlands and Hesperian plains are there. Okay, so then deposits like a delta, alluvial fans, layered sediments are there. There are many chaotic terrains are also there. Then a region having fluvial activity and Aeolian activities are also there. So these are the geological diversity of that Sante terrain. Now I invite Asif to continue with the Sante terrain.
Good morning, all. Before beginning with this, I would like to say that for the first time we are using this as Krishnan crater before a scientific community. So, like Dr. Rajesh has explained that we have selected Sandetira for several reasons to study. And when we observed this area, we noticed that this particular crater in this location is having a unique, distinguishable depth. If you look over here, this particular crater is more deeper than all surrounding craters in this region. And if you look over here, this low resolution image itself, we can see a lot of morphological features within this area. And this area was not studied yet. So we went for geological observation. And we also considered the fact that all the region like Ganges Chasma, Juende Chasma, etc., which are surrounded by this region is having a lot of fluvial related features. We can see some layered deposit that is in Juende Chasma and some hydrated signature from Ganges Chasma and all. So that we speculated that some kind of features would have been preserved within this region. And we checked for data availability from this region. And for validating our result, we did not have CRISM or Omega data for mineralogical studies. Where we identified some features within the crater. And this is CTX derived mosaic created from this particular region. And this is a crater which is having about a diameter 78 kilometers. So considerably larger crater within this particular area. And it is having a lot of morphological features like a discontinued peak ring complex from this like dome we can see, and terraced inner walls and some kind of deposits within this. These are some profiles we have taken from the crater. And this is a geological map we have created from this area, and from this we identified a lot of geological features that is varying from aeolian deposits to glacial derived deposits. And we have dated it using crater counting technology, and it is having an age about 3.5 billion years. These are some dunes present within the crater surface. We have identified from this area, and various kind of dunes are present there. And these are like transverse aeolian ridges, which indicating low energy aeolian activity. And come to the slide, and here we can see a theater head valley present within the crater wall that is leading to a channel, which in turn leading into a depression which is having layered deposits that we have seen already in Juende Chasma, similar kind of area, layered occurrence we identified here. And from valleys are leading to some triangular shaped deposits within the crater. And in different part of the crater, we identified these kind of deposits. Some kind of channel is leading to this triangular deposits. Like this is a deltaic deposit, something Steve has shown yesterday. That was a bigger one, but still we have more deposits over here. And we saw some ridges within the crater floor, and also we have some light-toned layered deposits. And some another features we have observed are some lobate flow features, which is also present on the walls of this crater. So this kind of features are present like almost all the walls, like surrounding walls of this crater. And this is a unique feature we identified and reported from this region. And if we look over here, we can see some lobate flow features are continuing. It is indicating like seasonal variation or seasonal melting of something. It may be like we have compared it with the terrestrial analogs. It looks like some glacial features in Antarctica. One flow occurred during melting we did, and after some time another melting has started. So overlapping features, superposed features we have identified from this region. We have high-rise coverage also from this region. And we identified from like another part also, two locations within this crater we have identified. And like we integrated this into a single diagram, all the kind of flow features we identified within the crater and compared with the earlier reported glacial features from the region. And this is a comparison with the terrestrial analogs. This is from Taylor Valley, Antarctica, the larger flows, like a similar scale of flows, rock glacier or glacier features. And these are like that overlapping or superposed features in like Mullins Glacier region, which is also having the similar kind of flow activity. And with these results, we published this in maps. And after the publication, when we published, it was unnamed. So there are like maybe experts may be knowing about these procedures. Anyway, after publication, we went for the naming process and all. The larger crater, the Krishnan crater, it is about 78 kilometer length. So when the crater is having diameter more than 50 kilometer, we have to name after a scientist who is deceased before 3 years, at least before 3 years. So like we want to name it after Dr. Kalam. We submitted the proposal, but it got rejected as he was a politician. So the political figure they won't accept. Anyway, we named it after Krishnan crater, after M.S. Krishna, Dr. M.S. Krishna. He was first Indian Director of Geological Survey of India. And some small craters which we believe influenced the morphology of this crater, which was also named after this place based on the rules, existing rules of IAU. After local places, which is having population less than 1 lakh, and it should be villages. So we have proposed several names. We have given our native place and all got rejected due to difficulty in pronunciation. So now it is not no longer unnamed, and this was all over the media, and we got national coverage. It was in Hindu, all the newspaper, all the national media, and the one of the crater was named after our institute, like the place of IIST, locality of IIST, and one is after locality of VSSC, and one is after the geological monument, Varkala, and one is after the Bakel archaeological structure, which is in Kasaragod district. So, and we have one plain over here, like, within the crater, which is named Krishnan Polus. Cutting this crater, a valley is also passing, like a meandering kind of valley is also, a channel is also there. It is named after Periyar, so the longest river in Kerala. And now the name is Echelon Mars. This is all about the presentation. Thank you.
Thank you both for that. Those really interesting and beautiful features that you've documented. I guess one of my questions is, if you think about a crater like that as a potential landing site, what is the new information in addition to what has been explored at Gale Crater, Gusev Crater? Opportunity has been going for many years, and now curiosity for many years with aeolian deposits, flow features, deltas. What do you think would really be a new addition in this?
I think area? Like comparing with this Gusev crater and the Zero, all these craters, we are having like glacial kind of features present over here, which was not there. Of course, fluvial features were there, but still, and these overlapping features, we think it is a recent development and seasonal and recent, because like there is no crater over this. Even small craters are not present. So some kind of recent activity is also going on there.
That's fine. That's a really nice observation. But scientifically, what will that add to our understanding of Mars? If in terms of going there to do science and technical analysis, what would be the real value?
Well,
I'm interested
like
to know
we,
your thoughts.
we believe like some kind of like water related feature that we can explore from this crater. Like we does not have these deeper craters surrounding this area. Only one crater is having like this depth in this area, and which will explain the fluvial or like water content in the subsurface area in that particular latitude. So that is what we believe.
Fortunately, we don't have that CRISM data from that one. Because of that, lot of evidence for water-related activity was there, but we couldn't identify like what are those alteration phases over there. If we could identify that one, so that can provide like a significance to biosignature or astrobiology-related point. So that is a one scientific target from this region if we are going.
And mineralogy, like it is difficult to study with the available data.
Thanks. I have a question, but I'm going to start with a comment, which is that the latitude and longitude of Jezero crater on Mars, that lat long is in southern India. So whenever I start up Google Mars, it always takes me to the middle of India because I have it defaulted to Jezero crater. So there's a fun fact that Jezero is in India as well. My question, though, is about Krishnan crater and how irregular its shape is. For a crater that size, I'm surprised at how irregular it is. It's not very round. And maybe I missed it, but I'm wondering what your interpretation is for its such a deformed crater shape.
I think like if you look over here, maybe I think because of this irregular structure, it was not studied earlier. And here, like we see one crater, which we believe that it triggered that flow structures within this crater. And we saw a lot of flow features over here, which are larger in size. See.
But even the upper left, it's sort of a diagonal straight line nearly. It's not curving in a way that you'd expect an impact to do. So I'm just, this is surprisingly sort of linear rather than, it really doesn't have this circular shape. And I'm just sort of struggling to understand how it might have, how it got that way. Is it all just post impact mass wasting, or is that's the only thing.
Yeah, that's what we also believe. These things we can see over here, these flow features. So we think that it happened after like post impact modification.
Okay, thanks.
So Vijay and PIL asked Krishnan crater located at the equatorial region, and how come the viscous flow feature related to glaciations can be found at this latitude?
Like there are some like very few reports. We believe that like they also believe that some glacial features, and this is not a vast glacial features. Only very few structures like glacial or ice related features we identify from this region. Only that much is even we know due to obliquity, some features that occurs in the mid to low latitudinal region, and we believe that kind of feature occurs.
I mean, I'm not an expert in the image analysis, but a quick question. I mean, as per the shape of that crater, is the straight line, the previous slide, is that because, I mean, is it possible to have a landslide or things like that later on?
Yeah, landslide is, of course, the landslide is occurred.
I mean, if you, after the impact, it eventually can.
Yeah, landslide is there.
Possible, isn't it?
There are dust storms. Dust storms are very on the surface. So now, if you think of the location which has been chosen, and you say it is energetically more turbulent, as energetically more turbulent, you are seeing a lot of actions being there. How safe it is for a landing site to be chosen at that location?
That I think a technical observation has to be made, and we have not climate people, we didn't observe that kind of things. Anyway, dunes are there, almost stabilized dunes. It indicates very active aeolian activity is not there.
Thank you very much for the presentation. For the sake of time, we will move on. Of course, we can have more discussions with both Rajesh and Asif because they're here. We have 2 online presentations coming up. The next one is by Alka Rani from IIT Roorkee, following which we'll have Satadru and Shobik. So Alka, could you share your slides, your presentation? Your screen is shared, but if you could go to your presentation.
So I just shared my presentation. Is it visible? Is it visible?
Yeah, please go to the full screen mode and get started.
Okay. So now it is a full screen, right? Can you see that?
Yeah, we can see your slides. Yes, please go ahead.
Okay. So good morning, everyone, and thanks for the opportunity for Dr. Sharma and Professor Chakravarti and all the organizers here for this opportunity. And this is my first presentation as a faculty because recently I joined at IIT Roorkee. And today, due to personal commitment, I couldn't attend in person, but I'm happy to be here with the Martian community. And thanks to the organizer CARE, because it's a kind of a big responsibility taking all the Martian community together and see what other people are doing and working together for the future Mom2 mission. And today I will be presenting how the volcanism can help us to understand the Martian secrets and how we will understand the evolution of the Mars. So today, before going into my research, because as we know that there are some new researcher and some enthusiasts who is not directly working on the moon or Mars. So before starting that one, I would like to introduce how our journey to the Mars has been started and what's going on and how much data we have, so everyone can access that one. So as since yesterday that you can see, this is the very common map that you can see that this is the physiographic map of Mars, and you can see there are like 2 features that we call northern lowland and the southern highland. And I can just keep out the pointer. And this is, if you see the topography of this one, so northern lowland is comparatively low in elevation as compared to the southern highland. And this is the kind of very big features that you see when you see the map of Mars. And the formation of this northern land and southern highland is completely different. And there are very different hypotheses that shows how the northern lowland has been formed. Seeing that it's a kind of flat, low cratered region where the southern highland is like full of the craters, and it shows that it is resurfaced or reason, and what is the possible resurfacing phenomena that we have. There are few things that there was an ocean, there was some volcanic activity that leads to the reformation of these northern lowland. So today we will talk more about like chemically how the northern lowland is evolved as compared to the southern highland, considering the geochemical analysis that we have from the remote sensing data sets. But do you like know that what is the very first picture of the Mars looks like? And I'm very excited because I have seen that during my postdoc in NASA. So that's what I'm excited to share about. So this is the unlike story of the first photo of the Mars, and this is a hand-colored version of Mars that we have from Mariner 4, which was the first successful Mars mission. And because it survived for a few minutes, so because the tape recorder got failed and they don't able to download the images, instead they'd have those data sets in the numbers, we call DN numbers, and they literally download those numbers and hand painted or like colored those versions with the crayons. And here you can see that there are like different colors that shows the different DN numbers and shows different information that they are seeing from the first image of Mars. But later on we have, and I got the opportunity when I visited JPL, that this was a image of the Mars, and I was very excited to share this one because before that I was not knowing that this is the first image that we have from my Mariner 4 instead of like particular image that we see today. So as we know that Mars is one of the explored planet from 6 decades, and we have more than 50 missions from the more than 10 nations since 1960s, and few are failed, few are successful, and few are ongoing. And you have lots of data sets that has been available to work on, and that can be like remote sensing data that is from inside data, and everything is there. So you can just go into the websites if you are excited about the Mars evolution and everything. And here there are a few like missions that I was naming because I was working on those missions data sets, and particularly I was talking about the gamma ray spectroscopic data sets. That is my main topic today, that how I'm using the gamma ray spectroscopic to infer about the evolution of Martian interior. So before going into my topic of interest, I would like to introduce few planetary sources that you can access these data sets that is freely available. That is, we have from the NASA, that's NASA PDS, and you can have all the target bodies that they have sent the missions, and you can download the data sets and play with that as per your interest. And our own ISRO has their science data archive that you can also access all the missions data sets from there. So it's very introductory websites that you want when you are starting looking for the other planetary bodies, that you need to have access to the data sets, and that where you can find the data sets. So you can go directly and explore those websites. So now coming to the topic, this is the first global map of Mars from Mariner 9 that we have from 1971. And here you can see that there are lots of like craters, and there are like mounds and some dark patches that you see here. So from there, you can see that like there is something different, and geological activity has resurfaced this Mars all over from north to south. And here you can see that from the MOLA data in 2000, I think 6 or like that, Exactly, I don't remember the number, but yeah. So this is the first time that we see that from MOLA that go give you topography map, this elevation map that shows that the Mars has the largest volcano of the solar system, which is of 21 kilometer in height, and which is, you can imagine that like the largest mountain we have is 8.8 kilometers. That is a mountain Everest on Earth, but we have the Olympus Mons that is almost 21 kilometer, thrice the size and height of Mount Everest. So you can imagine how big it is, and that is a volcanic thing. So. And here, my interest is the thermochemical evolution of Martian interior. And why I want to infer about that, because you see these geological evolution of Mars from each and everyone who is talking about how the Mars was active at the initial period of formations like Noachian, Asperian, and Amazonian time period. So Noachian is the oldest one and the Amazonian is the recent one. And here you can see that most of the activities like magnetic field and large impact craters, volcanic activity and the surface water flow and the warmer and the wet atmosphere that was very active in the early formation. But later on, all these activity, geological activity that we see today on Earth is like decreased or like extinct. But here you can see that the volcanism is a process which was very intense at the early formation, but later on it was decreased over the time. But it is still there, that few Elysium volcanic province is still ongoing and active volcanic provinces. Then we have some meteorites that also shows that the recent was in million years. So that's what my interest is, like how and what changes this happened, like it was active like Earth, but later on it was not. So that make us to infer about the thermochemical evolution, because if we know the interior conditions and interior chemical compositions, we can track back the history of the early formation of Mars. But we can do all these three based on three type of studies. That one is the remote sensing observations, and another was the in situ investigations of the rocks, especially the igneous rocks, which is a primary rock that comes from the volcanic eruptions that we have. And another was the sample or lab analysis, that is Martian meteorite. But all these three studies has their pro and cons. And here you can see that one, that remote sensing give you the global coverage, long-term monitoring, but we have a limited resolution and indirect measurement. So that is the limitations that we have from the remote sensing. But in situ, we have a direct observations, we have a contextual geology, but we have a limited landing size that I will show in the coming slide. And that is costly as per the remote sensing mission. A few samples, and the precise location of these samples is unknown. And here you can see this chart with the time scale, and you can see that there is a huge age gap, that we don't have any meteorite samples that is from 4.1 to 2.4 GA, and rest is few of them is like early pre-Noachian time period, but most of the meteorites that we have is mostly the Amazonian time period, and which is a kind of biased sampling that we are getting as a Martian meteorite from the Mars, but we don't know why it is. So it's an open question that we have. So why the volcanism is so important? Because you know that as a geology, it's a basic thing that volcanism is the only process that help us to get the samples from the interior of the planetary body to the surface, and that lava flows cool down, and we have rocks which we call igneous rocks, and these composition of the rocks we see on the surface is directly related to the pressure temperature conditions where it is forming and the depth at which it is forming. So if we study the superficial rocks that we from the remote sensing or like either sample or some in situ observations, that we can infer about the PT conditions at which it was formed at that time. So we can track the time period and the things that we want to infer about the interior conditions of Mars. And as I told you that the volcanism was active throughout its history, starting from Noachian to Amazonian, but we don't have the continuous observations or like written samples that we have from meteorites. Is like a huge gap that is basically very active time period, and we don't have sample from that. So it is kind of very unfair things that when we compare the remote sensing data with the meteorites that is comparatively younger than what we are observing from the remote sensing. So what exactly I did during the PhD, so I used the remote sensing observations to infer about the interior conditions. And how I did that one, I did 3 types of studies. First is geomorphic investigation of early volcanic provinces. I delineated that one, and after that I did geochemical investigation to derive the average composition of different age volcanic regions of using the elemental composition that we are getting from the gamma ray spectroscopic data sets. And using those average composition, considering the resolution, which is not equivalent to the in situ or the lab studies, but still we have a global coverage from the data sets. So we are using that elemental data sets to infer about the PT conditions based on the average composition that we have derived. But due to time constraint, that I will be talking more about how we have delineated the geochemical provinces and how we derive the average composition of different age volcanic provinces, which is kind of a study that I will be talking today. So as you know that Martian volcanic provinces are spread all over the Martian surface. And here you can see that Olympus Mons, Tharsis Bulge, and that is mostly recently, if you see from the remote sensing, they are Amazonian observations that we have at the top layer of the lava flows. And Elysium is also one of the youngest volcanism province, but Citrus Major, Hesperia Planum, and Melia Planum is kind of early Hesperian time period. So we have regions which are like from the different age volcanic provinces. But unfortunately, when we are talking about the landing sites, but no landing has been done on or near to that volcanic province. So this is a kind of biasness that I already feel that when you are comparing the data sets from the remote sensing to the landing site or in situ. And for the meteorite, we know that we don't know the specific location from where the meteorite is coming from. So that's a kind of thing that is a kind of gap that we want to resolve when we are doing the remote sensing, and looking forward to the upcoming missions. So when we talk about the geomorphic volcanic differences, then we have shield volcanoes, that is effusive eruptions, which is mainly happen in the Amazonian time period. But when we talk about the Hesperian time period, which is called Patera, that is relatively flat, and the pancake-like constructions that we have. And the recent observation for the early formation of the Noachian age period, that is explosive eruptions, and that is not forming the shield volcano. Instead, they are like very explosive, and they form plain style caldera complexes. That is the kind look like a crater, but it's not a crater. So that's a kind of recent study that from Michalski and Bleacher, which has proposed Noachian age volcanic provinces in 2013. And now I will go, would like to see whether geomorphically they are very different. Is there any compositional variations that we see? And is there any trend or relation that we see on these composition variations that we see from the volcanic provinces? So as we know, as I told that we have 9 elemental maps from the gamma ray spectroscopic datasets. And this is this is the 2 examples that I'm showing how it looks. So from these elemental individual maps that you can see the relative enrichment and depletion of particular element concentration, where it is enriched or depleted. For example, it is depleted iron in the Tharsis region and it is enriched in MMF region. But when you talk about the geological process, but you are not able to see how and what geological process is responsible for their formation and enrichment and depletion of these spatial variability that you see on each elemental 9 maps that we have. So that's why we need if we want to infer about the geological process behind these compositional variations that we see from the individual map, we need to infer about the element-to-element correlations, and that we did based on three stat multivariate analysis techniques. Why we are using three? Because we want to get rid of the biasness of any multivariate analysis techniques, and we want to see whether actually the provinces that we are delineating is coming out of the composition variation instead of like stat analysis that we are doing. So we use three at least, and the maximum two overlap we are delineating its final province. And this is the final consolidated geochemical province mass using the gamma ray spectroscopic datasets. And the four we are talking is like A, B, C, D here we named, and we are overlapping over the MOLA datasets. And the map that you see at the background is the geological map, because we want to see whether the composition that we are delineating is related to the age or not. So that's why we are doing the areal fraction of A, B, C, D provinces that we have delineated using the gamma ray spectroscopic datasets. So here you can see that the province D, which is kind of like the green patch, if you see. So if you remember the physiographic map of the Mars that you see here, that this is the lowland region, and which is clearly different composition from all the regions that we have from A, B, C, D, and that we will see in the coming slides as well. And when I talk about the age of these provinces, so province C and A is more of like older or Noachian and early Hesperian time period, but B is the youngest one, which is like Amazonian time period, that is early Amazonian, and that is falling on the Tharsis region that we already see. And the D is the late Hesperian region, and which is completely shown here that you can see. And we know that from the crater counting and all, that it is late Hesperian time period. So when we want to see how well our classification is, so when we plot this region A, for example, I'm just showing one example here, the lunar planum, which is very small region. And when we plot it over the geological time period, and here you can see that is early Hesperian highland, and which is very small patches, but here you can see that how very well that is distinguished from our technique and using the gamma ray, and it shows that the composition that we are seeing is directly representing the composition of that particular region, which is very distinct from the other regions that we see. So here, this is the, I don't want to go into this plot in depth because it's the kind of complication box whisker plot that is giving information about enrichment and depletion of particular region with respect to average Martian crust. So here you can see that one. Just to make you simple understand that one represent the average Martian crust composition, and with respect to that, how the region lunar planum is enriched or depleted. So it's, for example, here you can see that this region is completely depleted in H2O and potassium and thorium, but it is similar to that one. We have investigated two other regions, like the nearest region A and D part, like Acidia planitia and the lunar planum, which is completely overlapping with the geological region that we have. And another one is that SAP, that South Acidia planitia. And here you can see that this is our delineated map from the geochemistry, and which is very well delineated with the geological units, that is late Hesperian lowland region. And here you can see that one, the reason that lunar planum was low in potassium thorium, but when you talk about the Acidia planitia, which is enriched in potassium thorium and a little bit depleted in the aluminium. So this is how we can say that our classification from the techniques and statistical techniques that we are using is very well justifying our geological processes that may be responsible for these variations in the geochemistry. So now, according to, similarly, we have all the composition variations of these four regions, province A, B, C, D, and here you can see all the geological composition. Like, for example, that the province A, which is kind of an older region, like late Hesperian to early late Noachian to early Hesperian, and it is enriched in aluminium. But when we talk about the province B, which is younger or Amazonian, then it is depleted in aluminium. So this is how you can see that using those elemental composition, we can infer about the enrichment depletion of these regions, and we can infer about the geological process that might have resulted these enrichment and depletion in particular regions. So this is how we just delineated that one. And now we want to see how these composition is related to one to other. So we have a bivariate plots from silica to iron, and we have other two. And we see that all the regions which is lying in the southern highland follows a secular trend of evolution. For example, mid-Noachian to late Noachian is like enriched in aluminium and silica as compared to the Amazonian Hesperian volcanic province, which is province B, which is in Tharsis region, and it follows a trend. Like the box we have is like a spread of all the data points. But when we talk about the province T, which is a lowland region, it is not following. It's completely enriched in iron and silica compared to the Amazonian, even though it is like late Hesperian time period. And similarly, the trend was not followed for other element bivariate plot as well. So here you can see that aluminium and iron, it's not following the trend, but other regions which is following in the southern highland is following that secular trend and the evolution that we are seeing here. So from this, we can see that these regions are these regions are having an evolution trend, but we are lowland region is completely different evolution. So the key takeaway from this study is that the discrete igneous provinces that we have is the secular evolution pattern that we see in highland, but that is very different from the northern lowland, which is different evolution. And we see the composition trend has compositional heterogeneity in the secular volcanic provinces, suggesting the instinct primary process and mental sources. So as we can say that the evolution geochemically, we are showing that the southern highland is completely differently evolved as compared to the highland that we see from the gamma ray spectroscopy. Even the resolution is not that high as we have from the in situ and samples. So, but in future, we were looking, as I told, that we have very diverse rock compositions that we see from in situ meteorite and the composition from the remote sensing that we are not able to justify because maybe there is gap in the meteorite age analysis and all. So that is a biasness that we already have. So thinking that if we have our mission and that will be landing in the Noachian age igneous rock area, that will give you better analysis because we don't have that much sample from the Noachian time period. And all the craters and the investigation that we already have, the in situ one is mostly in the like Hesperian time period. So it's a kind of the biasness that we have and that we want to infer from our upcoming missions, and we will look forward to that opportunity. Yeah. And thank you for your time and kind attentions. Yeah.
That's the question.
Alka, you
Yes,
showed
ma'am.
H2O, right? So is this the
Yes.
WEH from the neutron part of it?
Yes,
I
ma'am.
assume it is.
Actually, we have the neutron spectrometer, and that is giving us
Yeah,
H
right.
component,
Right,
and
so-
it is a stoichiometric representation of H component into H2O. It's not
Right.
exactly the H2O.
Yeah, I understood. But my question was like, in your inferences in the later, how is that exactly used? Like, how does this water come into picture in this geochemical classification? I mean, is it
So-
part of some aqueous minerals? I didn't exactly understand. How do you take the water part of it into account?
So what exactly that we are doing is the delineating the provinces, which is kind of different composition. So we want to infer all the elemental maps together to make sure that the composition that we are having all the elements together in the stat.
Yeah,
But
yes,
when we
Alka.
are talking,
Yeah.
yeah,
Yeah,
when we
sorry.
are
Just the
talking
water part of it. I mean, we have read your paper, right? Like, understand
Yes.
your thing, but water, I thought, I mean, is it something independent or in the classification scheme, where does it exactly come?
So, because these are the elemental composition, we cannot directly infer about the aqueous positions. But here you can see that one that H2O is enriched in MFF region. So that may shows that there is a H component is high, and maybe the aqueous alteration and things is happening more in this region as compared, and the C region that you are the Merida planum, and you already have the Curiosity opportunity rover here. So they already find the aqueous altered minerals
Okay,
over
so
here.
there is also a correlation with the
Yes,
map of
yes.
aqueous. Okay.
Yeah.
Thanks, Sam.
I had a quick question, Alka. We
Yes.
had heard about talks on SNC meteorites yesterday. And of
Yes.
course, we have the chemistry of all these meteorites. Could you compare the chemistry of the meteorites, which are mostly coming from Amazonian time frames, with what you have presented, and maybe talk about the provenance of some of these meteorites from the surface of Mars? Is it possible?
No, actually, that's the reason that I was saying that when we are talking about the direct correlation of comparing the remote sensing data with the meteorite and in situ, so there is a problem that it's not completely overlapping. Just like the moon, we have a very good overlap, but for the Mars, there is a lots of discrepancy and lots of diversity that we see in the composition of these meteorites and the remote sensing data sets. And that's the kind of like a big question in Mars community that we are, why it is so, and what are the different processes that is leading to this type of diversity.
I'm just asking.
Yeah, well, I don't know. There were some comments about whether it's surface changes later since the meteorites came earlier, or is it just a technical issue?
It's more of like the resolution. First, I can say that the resolution is because what we see from the remote sensing is the upper surface layers. But when we do the analysis in the lab, we have it's like in-depth observations and the high resolution technology that we are using in micrometer scale. So that is the one thing. And another thing is that the samples that we have is mostly from the Amazonian time period, and which is still few things that we are overlapping, that like silica is low and the calcium is high in Amazonian, that is matching with few of the samples, not all. So that's the one thing that we already have. But not exactly we can say that, we have a shergottites, which is the igneous rocks, and completely overlapping with the observation that we have from the remote sensing.
Okay. Alka, we have one more question for you, but because we're running late, could you unshare your screen, and then we'll ask the next presenter to share the screen, and in the meantime, Professor Ghosh has a question.
Yeah, sure.
So it's a nice talk, very informative. So I have only one question, that you have time frame when you have large fluid action, and you have time when the fluid becomes, so there is a lot of fluid water interactions, or rock water interaction, or fluid interaction. Right. So how you take into account in terms of the primitive character of those materials at one locations compared to others?
So for that, we compare our data sets, like on Earth, we have a ternary diagram, we have CIA calculations, and we have a potassium to thorium fractionation ratios that we see. So we all compare all the in situ data set with the meteorite along with our GRS compositions. And we see that they all are following the same trend, not exactly overlapping, but it is following the same trend. So that's how we say that it's a primary composition or the secondary composition. Calculations, and we have a potassium to thorium fractionation ratios that we see. So we all compare all the in situ data set with the meteorite along with our GRS compositions, and we see that they all are following the same trend, not exactly. Thank you, everyone.
Okay, I think we'll move on. Thanks again, Alka. We will move on to the next presentation, which is again a two-author presentation by Sasadru Bhattacharya and Shauvik Mitra. Please go ahead with the presentation. Yeah, please go to the full screen mode and yeah, we can see it. Shobik, Shatadru, you can go ahead. We can. Hi,
Yeah,
Shatadru,
actually,
can
I
you?
think Shobik is actually sharing the screen.
Okay, yeah, please share the screen again, Shobik.
Shobik, you are not audible. Just unmute.
And the screen has been unshared again, so you have to share it one more time. Yes, we are able to see your screen. Please go ahead with the presentation.
Shobik, make it in presentation mode. Okay, I think there is maybe some problems because we are not able to hear Shobik. So if I am audible, then at the outset, let me thank the organizers, specifically Ramananda Sharma, Martin, for providing us this opportunity. And as a student of geology, accidentally brought the realm of planetary remote sensing or planetary geology. It was absolutely fascinating listening to the experts and the stalwarts of this field yesterday. We had wonderful lectures by Professor Rajamani, then Professor Martin, and I missed that talk of Professor Ruff, but we'll go back and listen to that. So it is absolutely, and then of course Devashish was presenting on the essential meteorites. And we could know that the Martian mantle is basically depleted in siderophile and so on and so forth. And lots of, future explorations are going to happen. So we are going through basically some extremely exciting phase, I would say. And with this, let me invite Shobik to start his part, and then we'll take on. Shobik, if you can start the presentation.
Yeah, no, not yet.
Okay, in that case, maybe I can try from my end. Yes.
Would you like to present it, Satadru?
Maybe we'll try. Okay, so I'm just.
So Shobik has to unshare his
Shobik,
screen
if you
and then
can,
you have to share it.
right. Shobik, can you unshare the screen? Or maybe if
Yeah, Shatadru, you can share your screen now.
Yeah, okay.
শুকনো থাকবে হাই
এর সাথে সাথে তোরও হয়ে গেল পুজো করে হ্যাঁ ফটো হ্যাঁ বাহ ইজ ইট ভিজিবল নাও তারা না করলে হবে না দেখলাম জল দিয়ে দেখাবো ইজ দ্য স্লাইডস ভিজিবল
You're able to see your
Hello?
screen now, so you have to.
Yeah, okay, fine.
Yeah, you can start with your presentation. Just click the presentation and.
I think it's fine now.
We are able to see your screen with a lot of files, but not the presentation yet.
Okay, I think it will take some time.
Shwatatra, in case you guys need a little bit longer.
Is it now possible?
Yeah, we are able to see you now. Yes, yes. Please go ahead.
Okay, fine. Thank you. Let me go into the screen. Okay, fine. Okay. So shall I start then? Shall I start?
Yeah, please start. Please start.
Okay. So thanks once again, and sorry for the glitch. We'll be talking about the terrestrial influence of Martian across environments in Kutch and Ladakh. Okay, so and it will be a joint presentation by Souvik and me. So let me, before starting this, let me acknowledge the team first. Okay, so in both these cases, we had a very strong team from the academia, and Souvik carried out his PhD on the topic of this Kutch and genocide under the supervision of Professor Shilbal Gupta from IIT Kharagpur. And also, the next part is actually the PhD work of Dr. Shubham Thakkar, and I am sure that he is present in the hall, IIC hall right now. And he is now pursuing his postdoctoral fellowship at IIC under the supervision of Professor Ramanand. So, okay, so this let me take you to the analog words from the western and the northern part of India. Okay, so I'll skip few slides, and it was an extremely enriching kind of an opportunity for us to hear to.
We've lost you, Shwatatra. We can see your screen. We cannot hear you. Shobik, Shatadru, what we're going to do is we'll give you some 15 minutes to fix the technical issues. Okay. We were planning to take a coffee break anyways. So we will join exactly in 10, 12 minutes. Can you fix the technical issue by then? Okay, yeah. So I'm here, Shobik, so just try. Yeah.
বলতে বলতে আমি নতুন ইয়ে থেকে আচ্ছা হয়ে গেছে। আমি 1 সেকেন্ড শেয়ার করে দেখছি যে এটা হচ্ছে কিনা। হ্যাঁ,
Ravita, am I audible?
এটা একবার দেখো না, এটা একবার
Hello?
দেখো যে হ্যালো, আমি শোনা যাচ্ছে?
Yes, now
Hello?
you are audible. হ্যাঁ
হ্যালো,
না না এটাই থাক, এখন তো ঠিক হয়ে গেছে। হ্যাঁ হ্যাঁ, শুনতে পাচ্ছো? বলো। তো,
হ্যাঁ আমি শুনতে পাচ্ছি। আমার কথা শোনা যাচ্ছে? মানে আমি মাইক অন আছে এখানে, এখানে যাচ্ছে? আচ্ছা আচ্ছা, ঠিক। এটা শেয়ার কি করে করবো দেখো?
হ্যালো সৌভিক দা, এবার তুমি একবার শেয়ার করো স্ক্রিনটা। সৌভিক দা শুনতে পাচ্ছো? কমিউনিকেট, মাইক অন করো। মাইকটা অন করো। Yes, your screen is visible now, but your mic is off. Turn on the mic. Please turn on the mic. Shobik da, turn on the mic. Now you, Shobik da, you are mute.
ঠিক আছে। আচ্ছা ঠিক আছে।
Hello Shobik da, make it full screen. Keep it like this. You
on করা
can
আছে
change the
সবকিছু?
slide
হ্যাঁ শোনা
and say
যাচ্ছে?
a few words.
Am I audible? এইখান থেকে কোনো শব্দ আসছে না।
Say a few more words.
এটা এটা করা আছে? হ্যালো, এইটা ইয়েটা সাউন্ডটা Am I audible?
Hi, you are audible, but you say a few more words. Please introduce yourself. We want to check the sound here.
Sorry, pardon, what to say?
You just read the title, please, for us.
Okay, okay.
We want to check
Okay.
the sound.
For checking the my audibility, is it so? The finding terrestrial enclaves of Martian aqueous environments in Kutch and Ladakh, India. Is it audible now?
Okay, is it audible? It is fine. Can you please check with Shataduda if he can join?
Okay, let me check.
Or you speak for him also. You can speak for him. Okay, see you in 10 minutes. Please
Okay,
wait.
yeah, thanks. এই তোমার কি ফোন আসতে থাকবে?
Bhavik, you may start now. Huh?
Shravika, you may start. Please go ahead. Proceed.
Should I proceed?
Yes.
Yeah. Sorry for the technical glitch. And I would like to thank to the organizers to giving me this opportunity to present my work in such a workshop. So I Shobhik Mitra, and along with my co-worker scientist Shatadru Bhattacharya, and we will show you how we have discovered the restricted Martian environment in Kutch and Ladakh area. So all we are interested now on Mars, and because of it lies in the Goldilocks zone. And Goldilocks zone is a zone which is conducive for life to sustain. And the primary aim of identifying the life is with some supporting documents, supporting evidences like the presence of water and the conducive environment like temperature. And therefore, we always try to find out this with the help of analog study. Analog study not only helps to find the life on Mars or other terrestrial planets, it also helps to understand how the evolution of the planets. So therefore, what are the terrestrial analogs, or what is the terrestrial analog of Mars? According to the Farr et al., it has several aspects through which we can find out or establish analog site on Earth based on the criteria, like the morphological criteria, physical aspects, chemical aspects, mineralogical aspects, climatic aspects, biologic aspects. Here we focus the mineralogical aspects, where we focus it on the hydrosulfur, presence of hydrosulfurs. And here, if we see the evidences of hydrosulfurs, the presence of hydrosulfurs on Mars, and as an analog, we supposed to choose the evaporite zone, the basaltic zone, and for example, there is the first analog site was the Rio Tinto, Spain. So why the hydrosulfurs is important as a Martian perspective? As we can see, we know that hydrosulfurs are evidence of the evaporites, the evaporation of water. And why the jarosite? Jarosite is another hydrosulfate that grows, that precipitates in a very restricted EH-pH condition, and it shows the actually limitation of the condition. So jarosite easily converted into goethite if it exists for the long time in association with the water. So this narrow, so the presence of jarosites therefore shows the evidence of the presence of water. It also indicates the oxidizing condition, and it also shows the very low pH condition. The mission Opportunity rover shows the presence of jarosite on Mars accidentally on the Meridinium Planum. The Meridinium Planum, when discovered instead of hematite, find the jarosite. They understand that there was some water on the Mars, and it is on the Barnes Formation. The Barnes Cliff shows the jarosite layers, about 10% was present along its layer, and therefore then after by several missions on Mars, it discovered the location of jarosite across the Martian surfaces, like on the Nili Fossi, Syrtis Major, Gale Crater, Jezero Crater, Meridinium Planum, and also in the Labyrinthis, everywhere. So we also tried to find out where this jarosite present on the Earth surface. So across the map on Earth, we found the jarosite everywhere on the surface. But the problem is the jarosite doesn't exist for a longer time and is easily altered into goethite. So what is the importance of Kutch here? Before our discovery, the jarosite on the surface of on the Deccan, the previous work showed, like on the Chitla and Govan, in the Matanumad formation, another hydrosulfate minerals, natrialunite. And the Greenberger et al. Shows a succession over the Deccan basalts that resembles the Martian basalt weathering. So therefore, on Earth, we first discovered the jarosite on a basaltic setting. Before that, it was mostly present on the felsic rock setting. So therefore, the main objective of this work, of our work, was to how this basalt plays the role to form this hydrosulfate in the Kutch area. In this study, we found the different localities where the jarosites are found, jarosites are present. It is mostly, this is the map of Kutch, and the western part of the Kutch shows the presence of jarosite. The greenish yellow segments is the Deccan traps, over which we can show the black dotted part, which are the location of jarosite. If we see in the bigger map, we can find that the yellowish part is the Deccan trap, and all the formations like in the Mathanumad formation, that is from the Paleocene area, Naredi formation from the early Eocene area, Harudi formation from the middle Eocene area, and Guneri formation, which is not over the Deccan traps, even it is the below the Deccan trap, that is in the Jurassic age, showing the presence of jarosite. And this is the location of Mathanumad, the first location, where this is the basement of the Mathanumad. We can see that Mathanumad segments is mostly covered at the basal part with the basalt of spheroidally weathered. And then eventually just overlying a kaolinite zone, which is altered from this basalt. All this area is covered with the columnar basalt, that is the unweathered basalt mostly. Am I audible? Okay. Here's some geochemical work on this basalt part, which shows that the basalt altered to smectite and then it's altered to kaolinite. So the diagram shows ACNK where the smectite zones it's transformed into the kaolinite. Just over this succession, we found on the peripheral zone of the basin a succession of laterite, bauxite, and some cells that is containing this mineral jarosite. Okay, and then in the deeper segments of the basin, we found in the Mathanumad in different layers, like in the cells, in the sands, and in the various tufaceous sands, we found this jarosite within the layers. In some segments, we found this jarosite cross-cutting the cells as a fracture. The jarosite is also present as a nodules in the red color. You can see in the right side of the image, the red dots, the yellow parts, the yellow dots as nodules, the jarosite purple are present also here. Now in the upper succession, that is overlying formation, is the Naredi formation. And in the Naredi formation, we also got this jarosite mineral, which is identified through spectroscopy and XRD. In this succession, we found this jarosite between the greenish shell and reddish shell with association with the gypsum layers. And these layers are not continuing in the Harudi formation, but in Harudi formations, within the cell layers, these jarosite minerals are present within the Cretaceous shells within the fractures. The underlying in the Jurassic age, this jarosite also found within the cells and as layers, and these cells are alternating with some hard crust lateritic zone. There are a few other locations in the Guneri formation where we can see the jarosite within the cells. Now the geochemistry part, we try to find out how this jarosite form. To understand that, we found that mostly these jarosites are restricted within the cell layers. So we collect all the cell layer samples and it's hosted jarosite samples. We try to plot and compare this. Here we can see all the cell layers are not matching with each other. But interestingly, the cell layers and its associated jarosite layers peaks are almost matching with each other. Like in the purple color, the Guneri PP, the RED pattern and the cell pattern in the Guneri location is matching with each other. The Mathanumad layers, cell layers pattern is matching with the Mathanumad jarosite layers. So similarly, we understand that this jarosite basically formed from this cell layer. The source of the jarosite to form was the cell. Now, using some stable isotope data, we conducted some isotopic sulfate isotope data, and here we found that from different horizons, from different locations in Nariti, Guneri, Harudi, and Mathanumat formations, we conducted the sulfur isotope data, and the 10 sample shows a wide distribution pattern. So it is hard to understand how jarosite is formed. So it's a kind of mixture of jarosite we get from the result. In general, if jarosite is formed from the seawater or evaporates, it shows 20 percentile to 21.5 percentile. But if it's formed from the cell pyrites alteration, it generally shows the -50 to 20 percentile. Here, the isotope data shows most of the samples of Mathanumat and Naradi show the lesser sulfur isotope data, that is showing the possibility of origin from pyrite, while the Naradi formation, while the Guneri samples shows in the other extent part where it is showing the higher value is indicating the presence of seawater. So it could be a mixture of seawater source or could be the pyrite source. So what is the implication of jarosite, presence of jarosite on Mars? So if we see, as it is widely distributed and its origins is quite complicated. So the main thing is the jarosite. The jarosite itself is its presence. Like on Mars, jarosite was presence of jarosite indicating the superficial water and the absence of water. Similarly, the jarosite on Kutch could have formed when the water retreated from its surface, and eventually in recent time or in the recent age, it could have formed on the surface. So I would like to request Shatadru Bhattacharya to continue the next part of how the jarosite, how the other analog sites is explained. Thank you.
Thank you, Souvik. You may go to okay, fine. Okay, so to further continue the studies of the jarosites of Mathanumat, of course, Professor Dijesh is not here, but I take this opportunity to present the work carried out by Dijesh, and of course, Shubham is there, Aditya is not here, and myself and Chandrika. So what he tried to do is that he tried to precisely measure the cell parameters of the jarosite. Am I audible?
Yes, you are audible.
Okay. So the thing is that he tried to do some kind of analysis with FE-cage Zanes to come up with the various jarosite related cell parameters, and also along with the XRD's analysis, and of course the VNIR spectroscopic analysis. And very recently, this particular work appeared in the last. This particular work actually appeared in American Mineralogist last year itself. And next slide, please.
Yeah.
Okay, so you can skip this. Already, I think yesterday Professor Martin talked about it. The L-tatio Chile and how good it is a perfect analog with respect to the home plate Gusev crater, and this digitated kind of nodular opaline silicas, they are extremely important from that point of view, and this is a landmark paper by Desbais et al. And okay, so we'll further move on to the next slide. Okay, so what we did is that we got interested after working upon that Deccan volcanic province, which is actually perfectly patterns in situ. We have Then we also try to look into the whole desert part of India. Before we look, which is extremely interesting and intriguing for any and for the apprentice is extremely to look at. And we in the sample the is geothermal regime what we see here is that we also is the nice paralysis side we have basically this is this from side which is
sorry, Shatadru.
And this
can you hear me? Very sorry to interfere. Unfortunately, I think there's an internet issue on your side and also on Shauvik's side because the slides are almost not visible and it's very poor audio. So would it be possible, because we are running late, would it be possible if we go on with the next presentation and I'll just message you separately about a time slot when we can actually arrange your talk again later in the day, today itself, okay? That will give you some time to, okay, because there's nothing visible right now, okay? Yeah, please stop sharing and I will message you separately. Sorry for the inconvenience.
For this.
So we'll move on to the next presentation, which is in person, and we will make sure that we hear Satadru sometime later today. So the next presentation is again a two-author presentation by Professor Nilanjan Dasgupta and Abhik Kundu. And over to you.
Okay, so good morning, everybody. I really thank the organizers to invite us and give this presentation. I, my friend, my collaborator, Dr. Abhik Kundu, will be jointly presenting it. Now, before going into the topic, I would like to dwell upon this word. Now, geology of Mars has got no meaning actually. Geology is for Earth. So let us call it areology. It's all scientific investigations of geological nature done on Mars, okay? So I deliberately put this point, and we both come with a structural geology background. Dr. Kundu has some sedimentological background as well. So our presentation will be mostly on the based on the structural and geomorphic features that we see on the surface of the Mars through remote sensing techniques. And what we can what information we can collect from those geomorphic features. Now, for the last 2 days, today and yesterday, we have been always switching between Earth and Mars. So that means we are doing some comparative planetology. That means we gain our knowledge from the Earth, we study the features on Earth, and then we try to see features on another terrestrial planet and try to correlate the features, thinking that the process being the same. Okay. So this is what we will be doing when we will be studying the morphological patterns and the grains, structural grains, and the cryosphere that have come up in the discussions quite often. All right. So, for example, if you look at these two photographs, these are wrinkle ridges traced, these are grabens traced. So just like we do for Earth, we make a cross section from the DEMs, and we can find out the dips of the faults. So we can make some paleostress analysis. We have done that. So essentially, comparative planetology means what I was discussing, that ultimately we try to formulate some qualitative, semi-quantitative, or even quantitative analysis of the morphological structures that we see on the other planets. The impact craters are one such, the most visible structures on any planet you look along. There are different types of impact structures, impact craters. And generally, Dr. Rajesh has also mentioned that these structures are useful in many ways. One most important thing is that they are actually chronometers. That the abundance of these, the sizes of these, the population of these, the density of these gives us an idea of the age of that surface. Now we drew whatever our mathematical formulations from the Apollo mission return samples and the surface study of the moon, and we extrapolated it for Mars, Venus, and other planets. So we have something which we call the production function, which relates to the number of craters that will be produced through time, and that has a variation through time. And we have another chronology function. I am sure all of you who are planetary geology people know these two terms pretty well. So what we do is we map a surface, we map the craters over an area, we count the number of craters, we make a size density population, we plot it, and we try to find out ages. And there are, on the basis of production functions and chronology functions, we have the isochrons. We try to fit our data and then find out a age for the surface with some errors, statistical errors. Now this is important for us because if we look at a structure, we would like to date that structure. Why would we like to date that structure? Because if there are superimposing structures, and if we cannot date the structures, we cannot say the temporal nature of variation of the structural pattern or evolution of the area. So that's why I put it here, otherwise I would have omitted. Now, when the structural feature is of an aerial nature, that means it has certain length, width dimension, we can go for the CSFD analysis. But often we find linear features, structural features like grabens or wrinkle ridges or some small faults, where we use this buffered crater counting method. It depends on the crater diameter, the buffering that we use, and this is also very common. It's not something that we don't know. Everyone of us use, whoever is doing planetary geology. And we also have used buffer crater countings in our publications as well. Now the craters that we see on the surface, we had an idea from the earlier lectures that they are either simple or they are complex in nature. Apart from this, if you consider the geometry, they are of varied geometry, okay? Some are circular, some are elliptical, some are Morse covering, some are flatter, some have central peaks. The peaks can be of 2-3 types. Of all these craters, one crater which interested us most is what we call the polygonal impact craters. The craters which have a polygonal natured boundary, so polygons. So you can see that this crater has sharp, instead of having a round thing, it has a sharp polygonal nature craters, and I will ask Dr. Kundu to take it up from here for analysis of these polygonal craters. After he finishes, I'll again take the mic from him.
Good morning, all. These polygonal craters, actually, they must have at least two straight segments along their rims and with an angle open towards the center of the crater. Now, we know that craters are divided into two types, simple and complex craters. So as polygonal craters also, they are divided into two types mainly. One is simple type. These craters are on Mars. These craters are less than 7 kilometer in diameter. They have a flat floor and a clean rim. Whereas these are the complex craters. This is also a complex crater. These craters are having boundaries, diameters more than 7 kilometers. They may have terraced rims, a central pit, or a central peak or a central pit. Now, there are several works on relation between polygonal craters and pre-existing fractures in certain areas. And authors have established that the polygonal boundaries, the trends of the straight segments of the rims are parallel or having some particular angle of 45 degree with pre-existing fracture planes, fault planes or joint planes in certain areas. And one classical example is Meteor Crater in Arizona, which is having almost square shape, and the trends of the straight segments of the rim, of the square rim, runs parallel to pre-existing joint sets of the area. There are also examples of experimental proofs, one by Agarwal et al. In 2023. They have shown that on foliated granite gneiss, if impactor hits, then the shape of the impact crater forms, that is polygonal. Now, in this comparison, if we try to examine the role of or the control of the fault planes on the polygonal crater geometry, we must exclude this type of polygonal craters which predates a fault plane. Here it is a wrinkle ridge. It is a ridge structure representing a fault propagation fold over a buried thrust fault. So we should be careful to exclude considering these types of craters following the law of superposition. For morphometric analysis of polygonal craters, we test the polygonality, actually the opposite to circularity, by this formula, where this is the diameter of the crater and this is the excavation depth. Obviously, the depth we can measure from the DEMs. This may not be the exact excavation depth because there are debris and sediments which fall over the floor of the crater after formation of the crater from the rims. This is Thaumasia minor area in the easternmost part of the Thaumasia plateau. We identified 45 polygonal impact craters in the area. And this is an area which is having numerous thrust faults and grabens. Thrust faults are represented by wrinkle ridges. There are some dikes also. And we have measured the circularity and excavation depth of these 45 impact craters. This is a relation between the crater diameter and the circularity. The circularity increases with decrease in crater diameter. Yes, it is approaching F1, it is more circular. This is the Thaumasia minor area, and this is an area east of this corporate rise. This part is the Thaumasia minor, and this is east corporate planum area. This area also has several representation, a geomorphic manifestation of fault planes. But the difference between these two areas in terms of density of fault planes and types of fault planes, that this has a single graben, this one. Whereas Thaumasia minor area has several sets of gravens. Sets are separated according to the trends or strikes of the fault planes. And we found when we mapped the polygonal craters, this area has a comparable areal extent with this Thaumasia minor. But we could identify only 12 polygonal craters in this area. So this is a question, the question arises whether the graben density controls the polygonal impact crater density, whether it is more graben, more polygonal crater, something like that. So then we matched, we correlated, we measured the trends of these fault planes. We measured the trends of the straight segments of the rims in both the areas, and we plotted the trends in the Rose plots. We found that in the Thaumasia minor area, the major trend of the straight segments of rims for both complex and simple craters is northwest southeast, and it matches with this, not a complete match, but no trend of fault planes matches with this major trend of the polygonal impact craters. Similar case is for the craters in East Corporate Planum area. So this indicates that because it is established that the polygonal crater rims are controlled by the fault planes, there are several papers on this, and so there must be some non-emergent faults, buried faults, which do not have any surface manifestation like wrinkled ridges, and they must be of, for this region, they must be north-south, northwest, southeast, and for ECP it is northeast, southwest. So these polygonal crater rims gives us some clue that there must be some fault planes or fracture planes or any type of structural weak planes which are not exposed in this area. So these are two publications, one for Thaumasia and one for East Corporate Planum. Now, then we tried to establish if there is any domainal or distance-wise control, the spatial control for these structural weak planes. We took, this is two representations we carried out for all sets of fault planes. This is a spread of north-northwest, south-southeast wrinkled ridges, and we took the center of this spread. The wrinkled ridges spread up to 300 kilometers from the center, and this is the spread of grabens of similar trend, and this is spread only about 150 kilometers from the center, and for different distances from the center, we plotted the trends of the polygonal crater rims. So we found that for the wrinkled ridges, there is a bigger correlation at the 150 to 300 kilometer and 300 to 450 kilometer. These black circles are the polygonal craters. And here we found that all these polygonal craters beyond, even beyond 600 kilometer, they are correlated with the straight segments along the graben rings. So we can propose that the spatial influence of normal faults, which are bounding fault planes of the grabens, they have more influence on the polygonal crater rims than the wrinkled ridges. And this is the publication on this work. Another important clue that the impact craters can give us is about the change of cryosphere with time. We selected again this Thaumasia minor region where we have several rampart craters. Rampart craters are the craters are surrounded by lobate ejecta blankets, which are fluidized ejecta formed. It is proposed that the fluidized ejecta forms with when the impact generated melt from the subsurface cryosphere mixed with the debris and flow outwards from the craters. And these are the ramparts. These are the lobate ramparts. And this is a single layered ejecta, and this is a multiple layer ejecta. There is another group which is called double layer ejecta, but there are proposals that double layer ejectors also form the similar manner with how the multiple layer ejectors form. And these single layer ejectors, these craters, they penetrate only the top surface of the ice-rich regolith, whereas the MLEs, they are proposed that these craters, they excavate beyond the lowermost level of the ice-rich regolith. So, these are the excavation depths we have measured, and diameter of the ejecta, diameter of the crater, it is measured to estimate the mobility of the ejecta, how far they can flow. And we also counted the craters on the ejecta blankets of the rampart craters to get the edges of each of these 32 craters, 32 rampart craters we studied for this area. And these are the edges. These are some representations. We have 32 craters there. And these excavation depths of single layer ejecta craters and multiple layer ejecta craters are plotted against their estimated edges. And we found that because the excavation depth, the lowermost layer of the cryosphere must be somewhere between the excavation depths of the single layer ejecta and multiple layer ejecta craters. So this really drawn line below the depth of excavation of the single layer ejecta, which is green dots, and these are the multiple layer ejectors. It shows that from Noachian times, in the early Hesperian times, the cryosphere was present in this area, and the lowermost level lowered down. So that means the cryosphere must have been thickened this part of the time, and it came upward. So it thinned with time, and this must have brought the cryosphere to the surface in touch with the atmosphere. I will request Professor Dasgupta to continue.
Okay, thank you, Dr. Kundu. What Dr. Kundu has tried to explain is that there are structural grains on the surface of the Mars, which influences the morphology of the features, geomorphic features that we see through remote sensing satellite. And this observation of ours, that it has come up close to the surface as time has progressed, has given us, has given us to think about that what could be the fate of that cryosphere if it actually exposes on the surface. Okay. Now this diagram has been shown by many in this conference, but this point actually is a very important point, which is the gravity, considering the gravity of the Mars and the atmospheric pressure of the Mars. There is a chance that if it comes, it will sublimate. It may produce a little bit of water, but it will sublimate. And Additionally, because of the obliquity, which has also been discussed in this conference before, we have these mid-latitude glaciations in Mars. Okay. Now, if we compare it with our glaciers on Earth, then we will find that there are glaciers at very high altitudes, which occupy very small amount of surface area of the Earth, and the other glaciers, which are less than 2 kilometers in height, they occupy the larger areas amongst the glaciers of the Earth. The same thing happens here as well, that this entire 30 to 60 degree latitudes north and south, they cover more area than actually the polar ice cap and the northern ice cap. So we were looking at one place, Protolinus mensa. This is an ongoing work. One of my scholars is doing this, and we were seeing some viscous flow features like this, which we all four types of viscous features. Now, this area is important in the sense that it falls in the dichotomy boundary of Mars, and it's a fretted terrain where there are mesa, and there are all sorts of scalloping and flow structures, and you will find structures like this where you have a flow pattern like this. I will discuss this in much detail in later slides. I'll not discuss on all these three in details, but this one will be discussed. So you have low-bed debris aprons, which I think Dr. Rajesh also mentioned. You have lineated valley fills, and you have concentric crater fills in the same area, which shows that, and the look of this picture shows that some mud is flowing like this. So it's a sort of a viscous flow feature that is evidence, and that has been proven also through experiments. Now, this form, which I want to discuss in detail, shows exemplary surface structure. So we mapped this glacier-like forms. We cannot call it glacier until we go there. Okay, so we call it GLFs. So the GLFs, we mapped one such GLF in this area, and you will find that there are different flows within this glacier. And there are different striations and many characters that mimic normal glaciers that we see in Canada, or we see in Antarctica, or we see in Greenland. And that has given rise to a branch of science called structural glaciology. So you see it in 2 dimensions, you see it in 3 dimensions, you see folds within the glaciers. So we are communicating our reports, but for just a presentation here, if you look at this part, you will see that there is a lineation, strong lineation. As you go down deep, you find the lineation continuing, but the lineation is very coarse here, but the lineation is very fine here. You will find boulders and pebbles with tracks rolling down from the flank to the main glacial valley. You will find crevasses, as you find crevasses within the normal Earth glaciers. Okay, you will find arcuate ridges, and these are flows which are superimposed flows. Maybe we are dating these flows. We are trying to date these flows, but at the end you will have this terminal moraine. You can count the boulders of the moraine, in fact, with high resolution images. So it all indicates that if there is a possibility of the cryosphere being exposed and water, this ice can come out as water, such glacial features can form. Now, at times, the glaciers on Earth gives rise to many large river systems, okay? But it's unlikely that such a large river system will be fed by Martian glaciers or Martian glacial ice. But still, in these mid-latitudes, we find plenty of river valleys. And in one such area called Noakis Terra, one of our students mapped the entire area. You can see whatever structural feature was available was mapped over a considerable area. And I would like to concentrate on the channels which are marked in blue in this map. They are very thin, I'm sorry, but you can see some of these here, some of these here. Okay. So our question was that what controls the flow of the channel? Is it the topography that controls the flow? or again, it's some embedded structure that controls the flow of the channel. So this is what we were asking ourselves, and we looked at the crater rims, as Dr. Kundu has said. We were looking at the crater rim geometry and trying to figure out whether the straight segments of the channels could mimic those crater rims. That means the crater rims could be pathways for the channel to flow. Or the second question was, are the channels flowing? They are independent of one another in their geometry. Are there any relationship between the flowage pattern of the sinuous channels? So for that, we did some statistical analysis, and we took the channels, 10 channels for study, varied geometry and different flow directions. We did some cross-correlation studies with some reference frame fixed on that place with nodes at specific intervals. We got the distances. We calculated the correlation coefficients. We found out the correlation coefficients for every channel with every channel for different nodes from Y1 to Y10. And if you look at this table, a part of this table for simplicity, you will find that there are two regions marked in these green boxes which has a very high correlation coefficient, while these have very low correlation coefficients. So that means that there are a set of channels which are statistically similarly flowing. And there are another set of channels which are themselves statistically similar, but dissimilar from the other set. So we could identify, we tested it with some statistical confidence tests, and we could identify the two distinct sets of channels or valley networks that were being guided by the structural grain of the area. One, these channels were being guided by the structural grain, while these were guided by the topography itself. So where depending on the topography, the channel geometry happened. So this is what we had done for the channel geometry and the structural control on the channels. We published it. We have a strong team, and we had plenty of support from ISRO. We must acknowledge ISRO for giving us 5 major projects for carrying out this work. And these scholars, very dedicated scholars to work with us, with mentors like Chauhan and Bhattacharya. I thank Ramananda Chakraborty, Dr. Ramananda Chakraborty, Madam Sharma, and Professor Martin for inviting us here and giving us the opportunity to express what we are doing back home. Thank you so much.
Thank you very much for the talk. It was really engaging, and the way you projected about the areography of Mars, it really gave us some good insight. Areology, yes. So my question is very specific to polynomial craters. So wanted to know whether these polynomial craters creation is completely due to impact, or there could be secondary processes which would give that definition to the shape. That is one thing. Second thing is, anything about the age of specifically these craters is known?
It's not polynomial, it's polygonal. It's shape, okay? So that's what we try to impress, that suppose there is a platform and a bolide hits, okay? So if there is nothing on it, then you expect it to be a circular thing. But suppose you have some fractures in it, okay? Now if you hit, then these fractures will take up some of the stresses, okay? And they will try to form a boundary of that crater. So if you have 2 or 3 different sets, that may give you a polygonal shape of the crater of the impact structure, okay? And for the second question is, I don't think there is any age constraint on it. It depends on.
Okay, thank you.
Yeah, in continuation of this previous question, It's a polygonal known that one statistics, what is it showing is maximum diameter is about 15 kilometer or something. All others are just below that. Is there any particular reason for that? Or is it specific to certain area, region?
It's specific to that area.
Okay.
Specific to that area. But you know, one thing is like, it depends on the spacing of these fracture sets. Now, whenever we have gone to the field on Earth, we see that there are master joints, there are parallel joints to the masters, very close spaced joints. Okay. But in these terrains, you have joints or fracture planes wide apart. So if they are close enough, then the crater size would be smaller. But if you have the provision of having distant joint planes which controls the geometry, then the crater size could be. It depends on the size of the bolide, number one, and then on the spacing of the joint planes.
For that region, we found that larger craters are towards one of the circularity distribution. Larger craters may be more circular.
I have a short question on the correlation that you had mentioned. Sorry, I probably missed it, but what exactly are you correlating? Is it like the flow direction? You said similar flows. So what exactly is the quantity that you are correlating?
Yes, we are actually correlating the flow direction of the channels. Okay. Now, if it's topography control, then the flow would be according to the topographic slope. Okay. Now, if there's a topographic slope like this and a topographic slope like this, then this channel will flow this way and this will flow this way. They will have no correlation at all. But if they are flowing in by means of some fracture systems, some structures are guiding them. We have rectilinear drainage patterns on Earth. So if they are guided by some fracture systems and there are different valleys like that, then those valleys which will be guided by the fracture system will have some sort of correlation in their flow geometry. That's what we are testing.
So we saw Krishnan crater earlier today, and I'm curious whether you think that's an example of a polygonal crater. I pointed out that what to my eye looked pretty straight segment. Do you guys think that?
We have not worked on that terrain, but yes, if there are at least two segments, one segment was pretty straight, not the other one. We need to check upon the fracture patterns and the structural grains of the area, a larger area on which the crater sits. So if we find some fracture patterns, and one such fracture pattern is actually along that boundary, then it could be a chance of a polygonal crater, yes. But I think they have done it. They can answer it better.
Sir, I think I have read your early words regarding this during my PhD times. And I had a doubt that, as you said, if something is there, this structure will be forming, like this polygonal structure. But what about this valleys, mountains and surrounding regions? There we already have a lot of lineaments on the surface. So inspired from your work, I have observed a lot of craters around that region. But I think there is not.
There is no fracture system.
No much.
Then.
But we have a lineament structure there now. Valley,
No, even, we generally think of fractures as joint planes turning out to be faults. But again, a wrinkled ridge is also a linear structure which has an embedded fault below. So not necessarily it should come up. Actually, we in our...
Try to match the head segments with the head segments around wrinkled ridge because they have thrust faults underneath. The ridges are folds over buried faults.
Basically, what fault bend folds sort of a thing which we have in.
I just have one question. So now, if you think of one image which you have used for your interpretation, if you take the image after a certain period of time, the same location, obviously you can see the kind of dynamic system which may be on. So did you try to do any such exercise where you have two images being taken for one site and you have seen any kind of, say, regime in terms of time where things are changing and how dynamic the systems are?
So for the crustal structural grain, they don't change much. But for the glaciers that I showed, yes. We found an image I didn't show. We found an image in 2005, another image in 2019. The boulder has come down and the lineations, they have been oversteepened. So we calculated, I did not mention, I showed the diagram, but because of time, I did not want to on it. We could measure the shear strain along that flow. There was a graph which red lines coming. So we measured the shear strain and it shows that there's a differential shear across both the glacial valley walls. So must be that one valley wall is a flatter valley wall while the other one is a very steep valley wall. So the shearing along the steeper one is more prominent than the one which is much more flatter. Yes, there's a time series thing we are doing.
Well, for the sake of time, I had a question, but I'll ask you lunch.
Okay, sure.
Maybe we can transition to the next talk, and
Thank you
I can
so
just
much.
quickly pose the question. Thanks again for the presentation. Could you comment on the depth of these fractures? Because if this is brittle deformation, that will tell you something about the rheology about this surface.
But if you have a radargram, you can at least find out at what level you have the ice and some streaks of fractures. So, but no.
The reason I asked is because if you go to the simulations of Melosh and others where there's a relationship between crater diameter and depth, and the depth of the crater is large enough. Right, but if we have these faults controlling, if these faults are controlling or the cratering phenomenon too, then they must be pretty deep-seated.
Maybe.
Which would have some implications on the rheology of the Martian crust because it's brittle deformation, right?
True. Maybe there's a possibility of that.
Thank you again. Yeah.
Thank you.
The next presentation is again a two-author presentation, although it'll be primarily presented by Shiva. I just thought I'll take 10 seconds to introduce the speaker because this is a special one. Shiva was a postdoc in my group, now faculty in presidency for the past 8 years now.
Yeah. Exactly.
And the co-author, Rahul, who is now somewhere else, was a grad student in my group. And so it's fun when I actually told them that, can you guys do something together? Because they did the work independently. And I said, why don't you guys present something together? So let's see how it goes.
Okay. Hello. Good afternoon, everyone. So I'm Shiva, and along with Rahul, we are going to present here, although Rahul is not present in person, on jarosites of Kutch. So in this particular presentation, I'm going to discuss about how the identification of this mineral, jarosite, change the status of the paleoclimatic significant basin of Kutch to a terrestrial analog for Martian process. Though this mineral has already been introduced to the audience by the previous speaker, but I will quickly just recap a few things that it is a hydroxy sulfate mineral from alunite supergroup having the formula of this one. So depending on what is there in the B site, whether it is aluminum or iron, it will be either alunite if aluminum dominant, or if it is Fe dominant, then jarosite. And depending on what is there on the A site, commonly it is potassium, sodium, and hydronium. We used to give the different names to it, like jarosite, natrojarosite, and hydronium jarosite. So in a binary compositional space, if we will plot Fe over aluminum plus Fe and potassium over Na plus potassium, then we can divide this particular supergroup into 4 different N members. Now, if someone wants to understand the jarosite in its entirety, how it forms and what is the preservation mechanism, then we have to look in this compositional space. The reason is, depending on how much aluminum is there in the system, its stability will change. Alunite is more stable in comparison to the jarosite. That is a K-bearing N member, then the Na jarosite, and of course, after that, hydronium jarosite. Now, the next question, why jarosite is significant, again, already introduced by the previous speakers. So I will give you a quantitative reason for that. If you see the number of publications in 3 fields, that is earth science, geochemistry, and environmental chemistry in recent years, then you will find there is a drastic increase in the number of publications. And it is not like that it was not known to us. It was known as a mineral associated with acid mine drainage. But something happened interesting in 1987 when Roger Bond basically predicted that jarosite alunite is present on the Martian surface. And this particular was verified around 2004. And then jarosite become a proxy for the availability of water, aridity, and also extend to the hints of the life. So that is why now, so there are a number of publications are there. So if we want to summarize few things which most of the articles agreed upon, then we will find it is a strong indicator of acidic oxidizing sulfur-rich environment. It has a limited stability. So if I will increase the water to rock ratio, jarosite will basically transform to magnetite, hematite, or goethite. Or if in your system, if you have plenty of calcium, then you will form gypsum. So it basically represents a brief episode of water activity, arid condition. The source of the sulfur for the jarosite on Mars is generally accepted as volcanic outgassing, though local sporadic pyrite occurrences are also reported. And it mostly present within the surface of the sedimentary layer, though fracture-hosted occurrences are also documented in literature now. And the last one is it is associated mostly with the basaltic rocks and the sediments derived out of it. Now, for a moment, if you just see the highlighted things, then you will find that everything is present in Kutch. That is why this is significant. Now, this geological map, again, shown by the previous author. So quickly, so most of the publications that we see on Kutch regarding the jarosite alunite supergroup, then we'll find they're mostly associated with Matan Umad. Now, but now we know that it is present in Naredi, Harudi, the geology, the younger sequences as well as the older sequence. Now, let us see the mechanism. So the first documentation was Chittal and Guven in 1987. They identified natroalunite. So we have to explain the source of sodium, aluminum, and sulfur. So they gave a very simple model that meteoric water interacting with the pyrite within the lignite, forming an acidic solution. Then it is basically leaching sodium from the surrounding rocks. And that particular solution, when interacting with kaolinite, basically it is forming alunite. But the condition is you have to remove the excess silica. And that is why they thought that they predicted that there should be an amorphous silica on the surface, but they could not get that one. And the other problem to discuss this model for jarosite formation is the kaolinite pathway is not required for jarosite because kaolinite can only give us aluminum, which is not present in jarosite. Now, the alternative model was given by Siddha and Kumar. This is a steam-heated model. So according to their, they also identify natroalunite and minamite, another member of alunite supergroup. So according to their model, basically the hydrothermal solution during the Deccan volcanism interacted with the volcanic ash deposit. And the sulfur, the source of sulfur is basically the volcanic gas and hydrothermal fluid. The interesting part of this particular work is that they noticed that these alunites are basically unaltered. So this is interesting because as we have already seen that they have a limited stability in the pH space, then how come they are unaffected by the meteoric weathering effect? So again, then the first documentation of the jarosite was by the Bhattacharya et al. Group. The previous speaker, Dr. Mitra and Dr. Bhattacharya, talked about it a little bit, and again, possibly they will present later today. So quickly, their model is the source of sodium, potassium, and the are mostly the seawater, according to this article. And the iron, aluminum can come from basalt weathering, and the source of sulfur is possibly pyrite. And they also put a question mark on that because in some of the locations where they found the jarosite, there were no presence of pyrite. So they speculated there might be some other mechanism. But again, the interesting part, they also noticed that these jarosite are very fresh and they are not affected despite they predicted their formation during the Cenozoic. So two recent publications came last year, that is again in the Matanu Mad. Dr. Subham Sarkar is one of the co-authors of this paper. So they also found the sodium jarosite in this particular formation, and they support supergene and hydrothermal, both the models of Chitale and Siddha and Kumar. And the model by the Dharya, they found some intergrowth of jarosite alunite, and they support hydrothermal process. And both these works actually predict that there might be the solid solution between the alunite and jarosite, but could not document because most of them was bulk chemical analysis. So now the work of the Rahul, though Rahul is not present, so I'm just presenting on his behalf his work during at IISc during his PhD with Professor Ramananda Chakravarti. So he also sampled from the Matanu Mad formation. He also observed the presence of the lignites, the source of sulfur probably. So the nature of the occurrence again support it, they are secondary in nature. But Rahul also sampled from Naredi and Harudi, which are basically geologically younger sequences than Matanu Mad. So the significance of this particular exercise is that the steam-heated model of Siddha and Kumar cannot be applied then at least for Naredi and Harudi. To identify the end members, he conducted the XRD analysis. So he found both the presence of jarosite and alunite, and also conducted the geochemical quantification of the iron, aluminum, the other ions, and found that these different regions, that is the Naredi, Harudi, as well as the Matanu Mad, they have different aluminum over the iron over aluminum ratio. So this indicates that these jarosites are possibly having some intermediate composition, possibly an indication of solid solution. But again, because of the bulk chemical analysis, this cannot be verified at that particular time. And he can then, to understand what is the source of the iron, he conducted basically radiogenic neodymium and strontium isotopic study. Now the modern day seawater value is around 0.7091. So based on that particular threshold, he found two different groups of jarosite, and based on the radiogenic neodymium, he grouped the Matanu Mad sample basically as a group 3, which possibly basalt dissolution is a source of iron, at least in this location. Then to understand the source of sulfur, he conducted the stable sulfur analysis, and it matches well with the pyrite known, and also the jarosite reported elsewhere in the world. And to understand that what is the contribution from the seawater and pyrite oxidized water, he basically conducted a mixing calculation. Now, as you can see in this axis, we have actually different strontium isotopic value, because we know that the open ocean seawater strontium basically changed in geological past. So based on that, he basically divided this one into two different groups. So the conclusion that we can make from here is that definitely seawater is probably a source of fluid and sulfur, and possibly different temporal regimes for jarosite formation. Because pyrite is a source of sulfur and also can be the source of iron, so to see that whether in any relation, so we can find a good correlation of radiogenic neodymium and sulfur isotopes. So this basically indicate that the source of sulfur and iron are same, whereas one of the samples showed, as I discussed earlier, of the Matanu Mad having highly radiogenic neodymium, possibly indicating the basalt as a source of iron. So to summarize his finding, It occurs both Mathanuma, the younger geological sequence. So probably there's hydrothermal explanation for the younger sequence is need evaluation. Simultaneous presence of jarosite, alunite, FeAl, probable solid solution. Pyrite oxidation, definitely the source of iron and sulfur in most of the jarosites, and seawater acted as a potential source of fluid and sulfur. Now, so this work that we conducted at Presidency University as a part of the project. So this is the work of my PhD student, Science and Go. So during this work, when we started, we first tried to see that what are the issues present and how we can solve this one. So jarosite, so one of the problems is that jarosite, though it is very less stable, still reported chemically unaltered. Why so? The second, when we conducted the field work, we found that when the jarosites are associated with the fractures, they are mostly remaining unaltered, but when they are exposed on the surface, there is the presence of the gypsum. So alteration is there, but differential alteration. And is there any presence of solid solution? The formation mechanism, where pyrite occurrences are not there, is raised by Bhattacharya et al. In 2016. And why, if the basalt is a source of iron or the other ions, then why it is not neutralizing the solution? And the other, the Chitala and Guven problem that why amorphous silica is not present on surface in Kutch, though their acidic weathering is present. So these are some of the field photographs. So this shows that the fracture-hosted jarosite and the co-occurrence of jarosite and gypsum. So it shows that differential weathering signatures. And we actually not only sample Naradin Harudi, but also from the Guneri member, that is a younger sequence. So again, that model of the hydrothermal cannot be applied, at least for these locations. So to understand what are the end members, we conducted XRD, FTIR, and Raman. And we observed that the majority of the samples are sodium jarosite, followed by hydronium and potassium jarosites. To see that whether any surface features are there of alteration, we conducted ACM study, and we found that at least some of the samples are very fresh. There are no alteration signatures. So definitely they are not altered. Now, another significance of this particular exercise is you can see that the grain size are maximum 5 to 6 micrometer. According to Madden model, if the size is around 1 millimeter, then jarosite can exist up to 500 to 1,000 years. Now, they are very fine, so definitely higher reactive surface area. Then how come they can sustain if they form during the Cenozoic era? So now the next one is the presence of aluminum in these samples. So you can see both the presence of Fe and aluminum. So when we conducted the EDS analysis, because the bulk chemical analysis will not be conclusive, we cannot identify whether this is a mixture of jarosite and alunite or it is an intermediate one. So we conducted grain-wise quantification, and we observed that basically most of the grains contain both iron and aluminum, and a perfect negative correlation exists between Fe and Al, which basically shows the solid solution effect. Another signature or the proof of that is, if you can see, this is the XRD peaks in the 2 theta range. These are the nitrojarosite peak, and this is the nitroalunite peak. Sorry, these lines is not visible here. So the peaks are basically shifted. If they are one end member, so you should expect all the peaks at either along these lines, but they are just shifting. The same is happening in the Raman. So this is, according to Maculum 2025, a signature of solid solution. So definitely solid solution is there in Kutch. Now, the source of ions. So we conducted a very simple exercise to look for the host rock composition, and we found that the sodium concentration in most of the samples, the host rock samples, are basically higher than the potassium concentration. And both sodium and potassium are there in the sample, so they can be sourced for the A site. And as far the B site is concerned, the sulfur is concerned, we conducted stable sulfur analysis for jarosite, pyrite, and gypsum. And we observed that the jarosite, this extent is matching with that of the known pyrite oxidation or the pyrite signature. So and also our jarosite signatures matches with the literature data. So this definitely shows that pyrite oxidation is a region. And here is another proof that if you see in those pyrites, so there are basically different alteration, the enrichment of iron and sulfur. So pyrite oxidation is the source of iron and sulfur, and alkali contribution is basically from surrounding lithology. Now the question is, where pyrite is not present, and what could be the reason for that, or how we can explain? So this is a map of, this is actually a photo of a lignite mine in that of Matanumad. And if you can see, there are major lignite mines are present in all these locations. So in the subsurface, we have enough pyrite to give this source for the iron and sulfur. And we also sample some groundwater to see whether what is the pH of that. And we found that in few of the groundwater, the pH level is around 3.5 to 4, which is highly acidic. So this is showing that these regions, definitely pyrite oxidation is a source. Now, if pyrite is present, then we try to look into whether is there any recent formation or it is ongoing process. So we sample, so because we visited this place 4 times, so when in one of the seasons we found that there is some precipitation of hydrosulfate mineral on this bank, and when we sampled this acidic water, this pH was around 2.9. We took the sediment, dried it, and see the phases, and they are alunite and jarosites are there. So that means this chemistry of the water is capable enough to give rise to the jarosite group as well as the recently forming. So now the formation mechanism. So we put everything in the geochemical model. We reacted the mineral with the pyrite equilibrated water and observed the potassium jarosite and Na jarosite can form in this situation. But the interesting part is that we observed that there should be some amorphous silica. On field, we could not get. But luckily, in 2 host rock samples, we observed 2 silica, the silicon oxygen bearing phases, where the silicon concentration is around 38, 35, and it is not. It is much lower than that of the quartz, because if it is quartz, your silica should be around 47. So definitely, this is the signature, and there is no crystallographic feature like quartz. So these are the amorphous silica. So now the question is why they are present in microscopic level, not in the on surface. As yesterday we have seen some of the field photos, and its region is the open system versus the closed system. If you have a fluid which is flowing together every time, and your water is reacting with that fluid continuously, or that particular, for example, the hot spring kind of situation, when the rock is getting exposed to the same fluid composition all the time, then this leaching can go on and you can form amorphous silica. But if it is a closed system, then the pH will be modulated because of the dissolution of the silicates, and then this will be restricted only in terms of the microscopic level. And so amorphous silica basically can be used as a proxy to know whether the paleofluid composition was flowing or it was a restricted condition. Now, to know that whether for understand the preservation mechanism, we basically synthesize the potassium jarosite as well as the sodium jarosite in lab, and also reacted with different pH and different water to rock ratio to see that what are the morphological changes are there and what is the change in the fluid chemistry. And so this is some example photograph. This is a synthetic jarosite. So after 1 hour dissolution, you can find in some of the grains, there are changes. After 2 hour dissolution, there are a lot of changes. So, but as I have already shown in some of the potassium jarosite images from the field, they are very fresh. So definitely dissolution is not happening in that locations. And another finding of this dissolution experiment is the decrease in the pH. We started with the pH of 6.5 and 7 or 8, and we end up after 30 minutes around 3.4, 3.5. So that means the pH of the solution is basically decreasing. And we tried with different water to rock ratio, 10:1, 25:1, every time the pH is decreasing. So that means your jarosite is basically dragging the pH. And according to the Madden model in 2012, the pH can act as a buffer. So this is possibly the reason that why within the fractures, we are getting very fresh, because in the fracture, water to rock ratio will be low. You will have a closed system. So that's why the pH will decrease to the stability limit of jarosite. But whereas you will have the surface, then the your flowing water, then you will find the gypsum or the hematite, goethite, those phases. And the other reason for the preservation is the aridity, as everyone is suggested. We got some mineralogical evidence of that, allonogen and tamarugite, two aluminum-bearing phases. They are basically known as a proxy of aridic conditions. So aridity and internal buffering basically stabilizing this one. So now the question is whether everything is known in Kutch. Answer is no. If we see this stability diagram, potassium jarosite is more stable than sodium. If we see this geochemical model I showed earlier, having a potassium is forming potassium end member of jarosite forming earlier. However, the potassium concentration is low. So that means if in a system you have potassium and sodium both together, and you will take that solution to a pH limit where jarosite can form, still your potassium will form first, then your Na jarosite or natrojarosite. So the question is, then why in Kutch we are having more natrojarosite? I don't know. We are looking this one through laboratory synthesis. And the other one is the shifting of the peaks. Because there we have the substitution of both in the A site, that is the potassium, sodium, hydronium, and also in the B site, Fe and aluminum in these samples. So we do not know that what is controlling this shifting of the peaks. So this is another thing that I'm trying to find the answer. So to find acknowledge so these were funded by the co-research grant of ACRB. This is my PhD student work, and Professor Panigrai, one of the co-author of this Guha et al. Paper recently accepted in JGR Planet. And of course, Professor Rahul Chakravarti will not only the guide of Rahul, also my postdoc supervisor. So these are the references. Thank you.
So nice talk, very exhaustive.
Thank you.
Okay, so now I'm glad that you measured the pH of the water during a time when it was most probably dry, when pH was 3.5 or something which you mentioned, or around less than 6.
On field? Actually, there are two kind of measurements. One was that of the groundwater. That pH was in some of the locations. pH was around 3 to 3.5. And near those where lignites are present, there are few water body accumulation. There the pH is around 2.8. So these are the pH ranges. And we also sampled during the monsoon to see. And during the monsoon also, we found that the pH is in the acidic domain, around 4 to 4.5 in few locations where the water is flowing.
So when you have interaction of a water which is having such a low pH during the monsoon time, obviously, you know that region is having a large buffer.
Yeah.
And the buffer is mostly carbonates. So how do you explain this observation that the pH range has never become alkaline during this time interval when there is a possibility of leaching of your silica, which is something anomaly which is unexplained?
Yeah. First thing, in Matanawad, if you see the setting, the basalt is present in one side and the sedimentary sequences are present in the other. That means in the vicinity, but not exactly where basalt is there. In fact, we could not find any jarosite near the basalt in that particular sequence. We observed gypsum. That means that particular solution that you are mentioning is reaching that location, but because of this pH problem, pH stabilization, it is forming gypsum, not jarosite. And we did the sulfur isotopic signature analysis of that gypsum. We found it is matching with that pyrite. So definitely the source of the sulfur is the same. And regarding why this is not affecting the entire region, because again, because its volume is insignificant in comparison to the other region. And second, when in monsoon, your water is flowing basically, so it is an open system. So the basalt will not be able to find the time to actually neutralize the solution. Unless it is a closed system where you have basalt and you have accumulation of water, this neutralization will not happen. With basalt, it is there. With basalt, definitely it is there, but it cannot neutralize that volume of water with short of time, because in Kutch, basically, your majority of the precipitation happens from July to September, almost like 91%, and the rest of the year is mostly dry. So within that small time, it is not possible for the basalt.
Follow that you invoke seawater, sulfur, when you are explaining your sulfur isotope.
That was actually Rahul's work.
Yeah, so seawater being sulfur being explained in terms of your relationship. You brought seawater as a way to explain your strontium and sulfur isotope.
If we see that particular plot, then it is basically sulfur in the in the x-axis, y-axis you have strontium, and when we plot our sample, that means when Rahul plot the samples in that particular mixing diagram, it is following that mixing curve. So the prediction is, because it is following the mixing curve, and you can find from one location to the other location, there is a difference. So based on that, the prediction is possibly your source of the strontium or sulfur can be the seawater. Yeah, sure.
Hello, sir. Great talk, sir, but I have one small question that in terms of oxidation mechanism in Earth and Mars, like in Earth, there is the oxidation mostly happens from the atmosphere, whereas in Mars, it is mostly related with the stripping of the atmosphere in that case, which is late Noachian, which is ideally, not late Noachian, late Hesperian, which is ideally dead in case of Mars, geologically dead. So how to correlate Earth analog, Mars analog in as a place in Mars, place in Earth?
Honestly, in this particular presentation, I try to focus on the process and to because to preserve the jarosite or this, your elemental behavior, your behavior of that particular mineral with reaction with the solution is not going to change. So that is the implication of this work. And when you are saying that what will be sorry, I didn't follow the first part, the oxidation mechanism. Because if we think that sulfur is basically the source from your volcanic outgassing, then also you that this particular pathway is applicable. Thank you.
Thanks, Shiva. Again, I just had a quick comment to make out here. So we are changing the schedule in the afternoon, okay? And so between 4 and 5, we now have a 1-hour coffee/discussion session to accommodate, an institute colloquium that has been given by our chair. So I'm sure there are more questions on jarosites, but I think there'll be enough time to discuss, between 4 and 5 p.m. So we'll quickly move on to the next presentation before we rush for lunch.
Sonia. Working now? Okay. Good afternoon, everyone, both offline and online persons present. And first of all, I would like to thank the organizers for giving this opportunity. I am quite new to this planetary science field, mostly working in the Earth. but what I am trying to correlate, what are the process that is similar between Earth and Mars, and try to understand Mars processes, particularly the alteration process in Mars from a Earth's perspective and other perspective. So as the organizers suggested to make it more pedagogical, so I kept some slides which is very basic. So I think that will be not that much useful for expert audience. So this work, I am from IITS in Dhanbad. So my institute supported a lot. Also, I had this ISRO Respond project. So that is supported through the ISRO Respond and also various DST projects through which this is supported. So just to start with, this has already been discussed, so I'm not going into this cartoon anymore. So the bottom line is that there are much similarities in the early processes between Earth and Mars in terms of their beginning and initial stage of evolution, at least till the period of 4 to some time later. So that we call to Noachian till the early Hesperian. Now, what basically interesting is that from that I want to point out that both had undergone similar kind of mineralogical and compositional evolution in the initial stage, in some part. So if I start from that part, so very basic. So this is my very fundamental basalt tetrahedron, where I am having the composition in the ocean or in earth that is mostly basalt, that is in your plagioclase clinopyroxene, this binary field, and in this triangle that is your plagioclase, olivine and clinopyroxene. This is the cumulate field as well as the other ultrabasic fields. Now if we look at the composition in the Mars, the initial Martian composition of the primary mineralogy, that is also mostly, if you see, basaltic in nature, and also there are few examples of moving towards the ultra basic in nature. So from a protolith composition or the bulk Mars composition, if we see, the mineralogy is basically basic. At some places it is your olivine bearing, means towards ultra basic component. And if we look at the chemical component system, it is CaO, MgO, FeO, Al2O3 and SiO2. This is the primary system that is having. Now, so with this initial, this has also been discussed quite widely yesterday, but just I want to point out something. So this is the period in the Noachian from where mostly these alteration things happened, and the this alteration that I will come, and this primary minerals, which in previous slide I have said mostly olivine, CPX and plagioclase, that has altered to a number of secondary minerals. And if we look at those secondary minerals in Martian, mostly phyllosilicate, silica, chloride, carbonate, and you are having hydroxysulfates. So just previous speaker spoke widely about the hydroxysulfates. In my presentation today, I will be focusing on the phyllosilicate part. So what after this initial alteration, next stage what happened? So this diagram has also been presented quite widely. So this is now our present day Mars condition just below the critical point of your water diagram. This is our present day Earth. So what happened at present? You are in this range from your ice to your vapor. You can have only this equilibrium. But earlier, when if you increase the pressure condition, if you can see that you can have all the three phases that are possible. So in Martian, early Mars, because the atmosphere was much thicker as compared to present day, we can have high pressure, as well as this is quite possible in case of the impact cratering areas where you are having high pressure condition, increase of pressure as well as temperature. But the main alteration that has happened, as I said, in this region. Now, if this is the main alteration part and the alteration phases that I have already discussed. So first, just as I said, the basic thing. So what is alteration? Just for the basic audience, it is the chemical and mineralogical transformation. So from a thermodynamic point of view, the G that defines the stability of a phase, it is governed by three factors. One is your pressure, temperature, and composition. Now, this composition in case of a fluid rock interaction means it is the composition of the bulk rock as well as the composition of the fluid. There are two components that are actually governing the composition evolution in case of your fluid rock interaction along with your pressure and temperature. Particularly if we look at the ultramafic system or ultrabasic system, unless it is very low temperature, low pressure, pressure does not have any role because the isographs are mostly vertical in nature. It is mostly the temperature and the X, T and X. These two are the main controlling factor in case of your ultrabasic system. Now, if we summarize the Martian alteration, there are four different types that has been summarized. Form one is called aqueous alteration. So these three aqueous, hydrothermal, weathering, just the difference is in terms of the temperature ranges, whereas acid sulfate alteration as well as the fluid that is interacting with that. Now, why we study this alteration? First, to answer this. So this diagram actually explains this. So now if we look at the areas in Mars where we are having these hydrous minerals or hydrated minerals, these are the areas where also we are having the enriched methane concentration. Okay. Now, that which proves that there is something which is linked between the presence of the hydrated mineral and the concentration of methane at that position. So this actually relates to what was there any time in past when there was a habitable Earth, because just in the next slide I will explain why. So just to give you, so yesterday we have heard more about the initial igneous history of Mars as well as the methanogenesis astrobiology perspective. What was main in this methanogenesis process is the reaction between carbon dioxide and hydrogen. Now carbon dioxide is coming from the atmosphere. Now the question is from where hydrogen is coming, because to initiate the reaction you need hydrogen in the system. So this is a cartoon diagram just simply to show the whole thing. So if you remember all the secondary minerals, be it your phyllosilicate, be it your sulfur salt, anything, all these minerals are having OH molecule in their crystal structure, most cases. So what happens if I just simplify the reaction? H2 actually divides into two components, H plus and OH minus. Now this is your primary anhydrous minerals, which is can be olivine, can be pyroxene, can be plagioclase, anything. Basically these are anhydrous. Now what mineralogically it is happening, in this anhydrous structure you are inserting some volatile component, and that component is your OH. Now while inserting this OH, you see when you are reacting with H2O, your H plus is left already from this case. So, and if OH is getting there, one electron is also released from here. Now in parallel to this, what is happening, in all the cases that I will again come later in a much detailed way, in these primary minerals, iron is present in a Fe+2 state. Whereas as you move to the secondary mineral, be it oxide, be it your phyllosilicate, even the jarosite also that we spoke of, there where iron is present as a +3 state. So there is a oxidation where from +2 to +3 it is happening. That is also releasing you one electron in the system. So this electron, when combined with H plus, that is producing the H2. And this is now very well established primarily in the terrestrial environment about the abiotic origin of life, particularly in the hydrothermal vent mid-oceanic ridge environment, where this H2 actually combines with CO2 and forms the CH4 or methane in the structure. So if what is the importance of this phyllosilicate or any hydrated mineral, then these are the sites where we are supposed to get H2 vis-a-vis CH4 in the whatever planetary or terrestrial body we are looking into. And that actually helps us to determine the future landing site for any kind of planetary exploration. So my perspective is to understand this H2 generation pathway from a combination of effort that I combine 4 approaches for our group. First one is your direct observations. So what direct observations can be? So either you can you can have direct measurement from the rover or lander. These are your direct observations. Or what can be done? There are samples that are coming from your extraterrestrial bodies, in this case Mars. As of now, there is no direct samples. So the only sample accessible to us are meteorites, right? So we can study the alteration process in those meteorites to understand the kind of alteration that is happening in those Martian environment. Along with this direct observation, we can see the analog samples. Why analog? As I said, be it any planetary bodies, terrestrial planets, fundamentally, mineralogically, it is the same mineralogical composition, be it olivine, orthopyroxene, clinopyroxene, and plagioclase. So the kind of parameters that will govern in case of your terrestrial condition should also apply in other planetary bodies, given the similar kind of physical and chemical environment is given. So just to understand those terrestrial or direct observations, we do experiment, because this is a really powerful tool, because whatever observations or analog, that is your past already things has happened. Now you are backtracking and interpreting. What we can do, we can actually simulate the laboratory condition where this kind of alterations are happening, and whatever your purpose is, you can identify or study those processes from a very fundamental level, how the phase evolutions are going on, how the fluid evolutions are going on, everything you can study. And finally, you can combine it with the geochemical modeling, because it is the thermodynamics and kinetics. These two actually play the role in governing the phase composition as well as the evolution in the fluid or any other product. So quickly, I'll just go through, but before going that, when we particularly come between Mars and Earth, 3 things, we can apply these things very well, but 3 things we have to be very cautious while applying the thermodynamic and kinetic concept. The temperature range in Earth is very restricted, whereas in Mars, it is widely spread out. So at least from minus 120 degree to this 20. So what it means, you are having a large variation of temperature in a Martian condition. Okay. Now, if you remember, as I said, this equation, when it is dependent on temperature, so if you change the temperature condition, it will have the effect on the phase. And likewise, the composition of Earth and Mars, this is widely quite different. Earth is more magnesium rich in nature, whereas Mars is already iron rich. Olivines are already iron rich. So if you remember the fundamental mechanism, what was happening? Iron 2 plus is going to iron 3 plus. So if the rock itself is more Fe2 bearing, there is a high probability if you just put water into it, higher magnitude of Fe2 plus will get converted into your Fe3 plus. So these two things you should remember. Now, the implication for this is thermodynamically, be it any planet, it will not change because it studies the initial and final phase. What will change is the kinetics of the reaction. At what speed the reaction will happen in a terrestrial condition and in your Martian condition. So this is our knucklite sample that we have actually collected, all three knucklites, Lafayette, Miller, and Uyamoto. So what I wanted to show you, the alteration features, which is more or less similar, where within the olivine, you are having some alteration veins that I will just come next slide. And these are particularly, if you closely look in the textural pattern of this alteration, particularly if you see particularly these patterns, these are typically governed by interface coupled dissolution precipitation process, it is called, where this is a fluid mediated alteration that is happening. Now, if I just zoom into this Lafayette image, this is that veins where these cracks are there. We have mapped this. These are basically aluminium rich saponite. We have done so this data is based on Raman as well as your EPMA. So these are your saponites that is forming within your olivine. So if you remember that in Martian surface, the most dominant phyllosilicate is your clay. It is not your serpentine that is present. And what we are trying to understand the origin of those clay and its applicability in hydrogen generation. So the same thing, now if I move forward, another image where you are seeing those saponites, which is associated with carbonates. Okay, so this is the image of that Lafayette, and this is actually iron rich, mostly siderite type this is. So we have observations where we can see from a micro scale, you are having a phase evolution from the reaction and interface from one phase to the next phase. And this is quite similar in case of your terrestrial samples, which we have collected from the central Indian ridge. These are ocean core complex olivine gabbro cumulate samples. So here also you can see, so this is the primary olivine grains. You are having the central actually clay minerals, and these are your, in this case, dolomite, because the iron content in the overall system is much lower. So the carbonate phase is different in case of Martian as well as from in case of your Earth condition. Same. Now you look at this. This is also another oceanic core complex sample of olivine gabbro. What I particularly want you to notice is three different interfaces in the whole sample. One is olivine plagioclase interface, another one is olivine CPX plagioclase interface, another one is single intra-olivine case. In case of your olivine plagioclase, you are having serpentine that is forming and along with chlorite that is forming. The same fluid, when it is in the olivine CPX plagioclase, it is serpentine as well as clay that is forming. Whereas the same thing when it is only in the olivine interface, clay is progressively becoming dominant in this case as compared to your serpentine. So what I want to just inform here, you keep the pressure same, temperature same, everything same. Only bulk protolith, the X that I have mentioned, you change from one interface to another interface. Because the X is changing, the phase is changing from one phase to another phase. So in one case it is chlorite, in another case it is only clay serpentine, another case is your clay. In terrestrial, particularly peridotite, olivine serpentinization is very common mechanism for H2 generation. So what our motivation was to check similar to serpentine can clay produce the H2, and try to understand this olivine to clay alteration process and what are the parameters that are governing this alteration process. So this is also another image of the whole sample. Also, I am just keeping this because this is also related to magnetite, the other component of this H2 generation. The same sample, some cases we are having magnetite, in some cases we are not having magnetite. The simple reason being, Fe2 in some cases is absorbed in the silicate component. When silicate is completely full, then only excess Fe3 plus is concentrating in terms in your Fe magnetite component, and that you can figure out in a simple mass balance equation. Now, to experimentally simulate this olivine to clay alteration process, this is the alteration that we have done. So this is the hydrothermal autoclave experiment. The instrument that were per reactor where we can actually simulate the reaction at variable pressure temperature, and we can change the reacting fluid as well as we can extract the fluid during the course of the experiment. Here we have tried with the San Carlos olivine, and this is the reaction product. What I want to show you, you see this is the pure olivine XRD. The moment the alteration we have done in, I think, 100 to 150 degrees for a short duration of time. So this is some peaks that have started. This is not fully developed peaks, some peaks that started to develop. And that is actually, if we just look in the micro images. So this is SCM, this is pure olivine. And you see on this olivine surface, these phases that started to develop, that is actually having, if we look at the peak position, this is less than 10. So that is representing the mica position, your clay position, but we are yet not confirmed. So we also did the TM of that same samples. This is pure olivine, and here you are seeing this is not fully crystallized phases, and you are not having any ACD diffraction pattern yet. So this is not fully developed yet. So some kind of amorphous stage it is, but we are going to continue this experiment to get the pure clay minerals. But at least we are in that transition. This is another experiment where we can increase the temperature at a higher temperature, because hydrothermal autoclave cannot go in that temperature. This is cold seal pressure vessels. So here what we can do, same experiment with diapside we have done with some aqueous solutions. And we have seen how the diapside is actually changing in its composition with effect to temperature and fluid composition. And you see it is first changing to talc and then changing to serpentine. This is also very common minerals that are found in all these alteration products. Okay, all are phyllosilicates. So along with this experiment, what we can do actually, during the course of experiment, we can directly measure the H2 that is coming out, because we have that experimental setup. So how throughout the course of experiment or the reaction, the magnitude of H2 as well as CH4 that is changing, that we can practically quantify here. Along with that, so once we combine this is we understand this through modeling. So just I will not go into much detail. So the bottom line of this whole 4 figures are that even if you keep pressure as well as temperature fixed, if you simply change the phase, the fluid composition or one chemistry in the fluid, you can shift from one phase to another phase. You do not need the change in pressure, you do not need the change in temperature also. And that is actually very insightful, because while studying this, we can study the alteration processes, the environment that has changed in the Martian condition or any planet in such a body. But this is a thermodynamic sort of situation where you will get the final product. What you can also do, this is the geochemical modeling part. You can also do the progressive reaction path modeling. So you start with a primary mineral, whatever rock composition, you do the progressive reaction, and you can see how the phase compositions are changing. With this, you can also plot the H2 variation in the system, given you have the Fe2 plus Fe3 plus concentration. So just one slide more, I'll just finish it. So if you see here, so I'm just showing two effects here. Here it is at fixed water rock ratio. That means both is 1:1. So in one case it is at 373 Kelvin. You see saponite is forming here. Okay, and the starting composition is your olivine gabbro. Now the same thing as I am going to higher temperature condition. You see the saponite is gone completely from this field, right? Saponite is coming now here. So it is starting much after the reactions are already progressed. So with change in the temperature that I have said, you can change the reaction product as well as the H2 production in the system. The other effect that I want to show you the water rock ratio. So this is at a 10:1 water rock ratio. Same way you can see you are having saponite here, the same clay mineral, and here both the cases I have modeled at 373 Kelvin. And if you see here, the production of saponite has actually, so you see from here, it is drastically going down. But as you go to the higher water rock ratio, your saponite concentrations are actually increasing. So you are basically producing more saponite. So just before I conclude, to supplement this actually now, I could not present it here because this is ongoing. So we are now going to perform the Fe2, Fe3 proportion analysis in individual phases, doing the TEM yields analysis. So what will give us throughout the compositional evolution, how the Fe2, Fe3 in the interface has evolved, because that will give us better quantification on the H2 production in the system. So in summary, what I wanted to just convey you. So before we try to understand the alteration process as a whole in any situation, your geochemical system, so what we can do, we can combine the first direct observation, because this will give you the ground truth, what has happened. Then you can correlate it with the terrestrial analog samples, because that will give you how it has normally happens in your Earth-like condition. Experimental study will help you to simulate those environments to give you better idea about what are the controlling factors in case of such fluid drop interaction process. And then finally the modeling that will give you better idea about the phase evolution from a thermodynamic perspective. So once you combine all four, you can study any fluid drop interaction process in a better way, be it in terrestrial environment or be it in any other extraterrestrial bodies. So that's all actually. So this is my, so first, as I said, I want to thank the ISRO Respond, because this is most of them from ISRO Respond project, as well as initially I was at DST Inspire, so Inspire Fellowship, as well as the IIT ISM Dhanbad grant. Various national and international collaborators from my PhD onwards, so it's a 15 years journey, as well as all the doctoral and master students. And that's it. Thank you.
Okay, we can, so we are, kind of a bit late, but we can take a quick question. But remember, we have more questions around 4 to 5. We can have a extended discussion session. Sure.
Your starting material, you did the interaction with water. But if you think of Martian, any kind of water is saturated with CO2. So your ideal example will be to have CO2 being one of the factors, being there to introduce your water rock interaction and try to see the formation.
So you are absolutely right. So we are doing it because XCO2 means XH2, H2O CO2 proportion binary will have a definite control, because if you look at that carbonate formation, from silicate to carbonate, it is changing because in the fluid, your H2 proportion is already decreasing. So XCO2 is increasing. So, but the point we have, so this is actually lab we set up. So we started to do with the H2O part first. We have the CO2 already there. We are doing the olivine to siderite alteration also, but that result I have not shown. But you are absolutely correct. We have to include the CO2 into the system. Okay, thank you.
So I have a quick announcement. Actually, so our volunteers have arranged a photograph session. I mean, just a quick photograph before everybody moves for lunch. Okay, then we will do it at 4 o'clock, perhaps. Yeah. Thank you.